effettivamente sarebbe utile.
Okay, so Cesare is telling me we are online and we are going live on the YouTube channel of the Centro Research Center E.Piaggio. So welcome everybody to the second day of the Robotics Research Jam session. And today we will have distinguished panel of speakers starting from Carlo Trompetto, Department of Neuroscience, University of Genoa, Andrea Davella, University of Messina, Lorenzo Masia, Heidelberg University, and after the coffee break, Lorenzo Sabattini, University of Modena and Reggio-Emilia, Dimos, Dimarogonas, KTH, Royal Institute of Technology, Stockholm, and concluding with Paolo Salaris, University of Pisa, Italy. So it's my great pleasure to leave the stage to the first speaker, Carlo Trompetto, that will speak about the rehabilitation of spasticity, spastic dystonia, and co-contraction in the subacute phase of stroke, the aid of robotics.
Okay, I have to share the screen. No. Sorry. Condividi qua. Sì. Ok. No, esco qua.
Di nuovo?
Qua.
Sì.
Ok. Can you see the slide?
No.
No?
We see another video probably.
Another video, so.
Or there's written that you have to start an application.
Ah, ok. So, sorry, condividi, share. Qua, no? Share video, desktop, ok.
Another video probably. Another video.
Oh, okay.
Or there's written that you have to...
Now you can see the slide?
Yes, I see the presentation.
Okay. Perfect. Okay. Good morning, everyone. First, I want to thank the organizer of this meeting for inviting me. It's a great pleasure and a honor for me to have the possibility to talk you about the rehabilitation in the subacute phase of stroke. I will show you some very preliminary data suggesting that robotics could be useful in preventing a number of clinical signs which can cause disability, known globally as the positive signs of the upper motor neuron syndrome. The subacute phase, the stroke, I mean the first 3 months from the acute event, these very narrow windows, is the most important phase for rehabilitation. In this phase, the plastic changes in the central nervous system underlying the recovery of function are very active. For these reasons, the most consistent part of the recovery of the function occur within these first 3 months of stroke. Then, after the 3rd month, we can have further improvements. However, these improvements are certainly less important than those that occur in the subacute phase. This is the Polyclinic Hospital of San Martino, and this is the clinical of riabilitazione, di neuroriabilitazione dell'ospedale Policlinico San Martino. Our primary mission is to rehabilitate patients suffering from stroke in the subacute phase. The patients admitted to our unit come from the stroke unit of the polyclinic. On average, they have had a stroke 1 week, 10 days when they are admitted in our unit. We admit about 200 stroke patients per year. The stroke patients, the clinical sign that causes the greater disability, there is no doubt about it, is the loss or the reduction of voluntary movement. This clinical sign is often referred to as muscle weakness, motor deficit, or the more correct name is the central paralysis, because it's due to the disruption, dysfunctioning of the upper motor neuron at the level of the cortex. In the rehabilitation of these clinical signs is that induce the much of the disability. In the subacute phase of stroke, it is essential to promote the recovery of voluntary movements. In this attempt, our most important weapon is the therapeutic exercise. In the rehabilitation of the upper limb, the motor tasks involving object manipulations are very, very important, very useful. First of all, because these movements are pivotal in the activity of daily living. They guarantee the proprioceptive information from the affected limb to the central nervous system, and the proprioceptive information in turn increases brain plasticity. Furthermore, they are likely to activate the mirror neurons, which are active during the observation of the gesture, the imagination, and the actual execution. And last but not least, these movements increase patient motivation. Stroke is the most frequent cause of the upper motor neuron syndrome. Other causes are brain injuries and multiple sclerosis. The upper motor neuron syndrome is the complex set of clinical signs due to the impairment of the descending motor pathways, which connect the motor cortex to the spinal cord. As I told you, the most disabling clinical sign of upper motor neuron syndrome is undoubtedly the deficit of voluntary movements, the central paralysis, and much of the rehabilitation efforts in stroke patients in the subacute phase are aimed at recovery central paralysis. However, upper motor neuron syndrome is not only constituted by the deficit of voluntary movements. The upper motor neuron syndrome also includes the so-called positive signs, which are characterized by an excess of muscle activation. It is an involuntary and inappropriate muscle overactivity, which can cause disability. Such clinical signs include spasticity, which is the most famous signs among the positive ones, but is not the more disabling one, spastic dystonia, which is very disabling, and spastic co-contraction, which is very, very disabling. These positive signs, this involuntary and inappropriate activity, is caused by the exaggeration of the spinal reflexes due to the increase in spinal excitability induced by the injury of the descending motor pathways. The lower motor neuron in the spinal cord can be activated not only by the upper motor neuron, but also by inputs coming from the muscles and the skin through the spinal reflexes. In the patients with the upper motor neuron syndrome, the descending motor pathways, I mean the first motor neuron, are damaged by the lesion. The system or the reflex movements, on the other hand, is not affected by the lesion. Although not anatomically affected, spinal reflexes undergo important functional changes in stroke patients due to the increase in spinal excitability induced by the injury of the upper motor neuron. This increase in spinal reflexes causes the positive signs of the upper motor neuron syndrome. They are frequent in the upper limb, as you can see in the picture, where they involve mainly the flexor muscles, most of all the wrist flexors and the fingers flexors of the upper limb. Let me show you these clinical signs. Plasticity is the exaggeration of the stretch reflex. In healthy subject, stretching the muscle when the subject is relaxed does not induce reflex EMG activity. For instance, if you extend the forearm on the arm, as in this experiment, which was made by Tillman in 1991, and we record the activity of the biceps, we cannot find any EMG activity. If you want to find some EMG activity, the stretch must be very, very fast. The situation is completely different in the patient with spasticity, where also slow passive movement can produce a lot of reflex EMG activity, which is experienced by the examiner as an increase in muscle tone. Very often in the stroke patients with the upper motor neuron, muscles are spontaneously activated. This EMG activity is not caused by the elongation, the passive stretch of the muscle, but is spontaneously. Though the patient is not only unable to voluntarily activate the motor units, and therefore he or she presents the central paralysis. At the same time, the patients who cannot activate the motor units is not even able to relax the muscle, which remains tonically active. This condition is called spastic dystonia. It's very frequent at the level of the upper limb. It causes a lot of disability, and it can determine the assumption of abnormal postures and greatly limit the voluntary movement. So spastic dystonia is a very disabled sign, much more disabling than spasticity. Another very disabling sign is co-contraction. For example, the patient trying to extend his forearm, he can activate the flexor muscles. However, the simultaneous contractions of the extensor muscles block the movement or even induces a movement in the opposite direction to that desired. It must be considered that these positive phenomena, spasticity, spastic dystonia, co-contraction, emerged in the subacute phase of stroke. When the patients, 7 days after the event, 10 days after the event, arrives in our unit, they do not have spasticity, do not have spastic dystonia. But these signs emerged in the subacute phase of stroke. And this because they are the results of plastic changes in the brain. Plastic changes, which are very active in the subacute phase, do not produce only the recovery of voluntary movement, adaptive plasticity, but also cause the development of the positive sign of the upper motor neuron syndrome. Therefore, there is also a form of maladaptive plasticity, and spasticity, spastic dystonia, and co-contraction are examples of this maladaptive plasticity. An important point that must be considered is the progressive. An important point underlying these positive phenomena is the progressive increase in the excitability of the lower motor neuron. This is a form of plasticity which is responsible both for adaptive plasticity and maladaptive plasticity. This phenomenon, the increase of the excitability of these cells, the lower motor neurons, is due to the denervation hypersensitivity of this cell and allows the lower motor neuron to pick up the weak signals coming from the cortex, coming from the upper motor neuron, damaged by the lesion. This obviously promotes the recovery of strength. At the same time, this phenomenon, however, the progressive increase of the excitability of the lower motor neurons, increases the excitability of the spinal reflexes, leading to spasticity accompanying. The fact that the mechanisms of adaptive and maladaptive plasticity are, at least in part, the same It explains why the motor task involving the activation of flexor muscles at the movements, including grasping and manipulating objects, can worsen the positive phenomena, because the movement increase the level of the excitability of this cell, which is responsible both for the recovery of the voluntary movement and for the positive signs of the upper motor neuron syndrome. This often limits the use of such motor task in the subacute stroke patients. In the clinical practice, if the subacute patient begins to manifest spasticity, spastic dystonia, co-contraction in the flexor muscles of the upper limb, we tend to avoid the motor task with object grasping and manipulation. We concentrate our work on the trunk, shoulder, and the lower limb, and we try to promote the plasticity acting at the cortical level or at the level of the basal ganglia using motor imagery and action observation. We don't want to stimulate the lower motor neuron innervating the flexor muscle with the real movements. So we prefer motor imagination and action observation. This choice limits the emergence of positive phenomena. In doing so, however, we're likely to be less effective on the negative phenomena, less effective on the central paralysis. It is the classic too short blanket. The situation could change thanks to this fantastic robotic hand, the soft hand X, thanks to the collaboration with Professor Bicchi and his co-workers at the Italian Institute of Technology. We have been able to use this robotic hand in our patients, in our stroke patients, in the subacute phase. The hand can be controlled by the subject in different ways. One of these ways is by the residual movements of the fingers of the affected hand. For our purpose, the hand, I show you the video, was set in such a way that to extend the fingers of the robotic hand, the subject extends his own fingers. But now, to grasp objects with the robotic hand, the patient does not activate his fingers flexor, because if he keeps his hand relaxed, the finger of the robotic hand closes into a fist. Hence, the subject voluntarily activates his finger extensors to open the robotic hand. To flex the fingers, on the contrary, he has to relax his own hand. With this method, we can make the patient grasp and release object by activating only the extensor, but not the flexor, which are those impaired by the positive phenomena of the upper motor neuron syndrome. In doing so, we hope to take the advantages of the goal-directed motor task, including grasping and manipulating movements, without the associated disadvantages. I mean, without activating the lower motor neurons, which is involved in spinal reflexes. The subject performed the movements under EMG control, this to make sure that he or she activates only the wrist and finger extensors during the task with robotic hand without activating the flexors. We use this protocol in 2 stroke subjects in the subacute phase. In both subjects, this is a very important thing, spasticity was under development in wrist and finger flexors. Both of them showed an incipient, a beginning spasticity at the level of the fingers and wrist flexor of the upper limb. For these reasons, in these two patients, we would never have thought of using motor task in which the patients had to grasp and drop objects. This in order to prevent the increasing of spasticity. These preliminary experiments, we verify that the use of the robotic hand, as illustrated in the video, activation only of the extensor muscle, does not worsen the positive phenomena in flexor muscles of the wrist and finger. The treatment had a duration of 2 weeks, 10 sessions of about 40 minutes each, 5 sessions per week. During the 40 minutes of each session, the patient was trained to use the robotic hand. The patient had to grasp a release object of different sizes and of different consistency. The subject was also asked to move this subject from one position to another. As outcome measure, we use the modified Ashore scale for wrist and fingers. In this scale, 0 means no increase in muscle tone, 1 means slight increase in muscle tone, and 4, the affected part, is rigid in flexion and in extension, so it is not possible to mobilize the joint. We also assessed the stretch reflex in the wrist and finger flexor using surface EMG. This is the most precise sensitive measure of spasticity. In fact, spasticity is a tonic stretch reflex. We also assessed the ability to perform voluntary flexion and extension movements in order to evaluate the possible presence of co-contraction. As a measure of motor capacity, we use a box and block test. However, these preliminary experiments are aimed not to investigate the increase of the movements, the recovery of the movements after the treatment, but were aimed at verifying that the use of the robotic hand does not increase the positive phenomena. The time course, T0 before the starting of the first session, T1 after the 5th session, T2 at the end of the treatment, and T3 7-10 days after the end of the treatment. 2 patients were evaluated. The third patient is a 57-year-old woman suffering from a serious hemorrhagic stroke affecting the right hemisphere. The treatment with robotic hand was started in the middle of the sub-acute phase, about 40 days after the event. In the day preceding the treatment, as I've already said, the patient was developing spasticity in flexor muscles of the wrist and fingers, with a mass scores of 1 at T0 before the treatment. The first EMG, the first trace, the EMG trace referring to the flexor muscles of the wrist. The second trace are the flexor of the fingers. The third, the extensor of the fingers. Then the fourth trace record the movements of the wrist by means of an electronic goniometer. The passive manual extension of the wrist performed by an examiner was performed in 1 second in order to evaluate the tonic stretch reflex in the muscle of the wrist and fingers. The tonic stretch reflex is not present in healthy subjects because in healthy subjects we need much movement more with increased velocity to activate the reflex. So this EMG activity is a pathological EMG activity in the tonic stretch reflex, which is the phenomenon producing the spasticity. I mean, which is the muscle hypertonia. So at T0, before starting the treatment, the tonic stretch reflex was present in flexor muscles of the wrist and the flexor muscle of the fingers. The reflex was smaller at T1 after 5 sessions of treatment and disappeared in the subsequent evaluation. So spasticity was present before the treatment and disappeared during and after the treatment. This slide illustrates in the same patients the ability to perform voluntary alternating movements of wrist flexion and extension. This ability to perform voluntary alternating movements was present before the treatment, and it remained unchanged in the subsequent evaluation. So there is never co-contraction. The second patient is a 58-year-old man suffering from a right hemispheric, this time ischemic, non-hemorrhagic stroke. Even in this case, the treatment was started in the middle of his subacute phase, 2 months after the event. At the other subject, he was developing spasticity in flexor muscles of the wrist and fingers. The reflex was present before the treatment at T0, it's a pathological activity. It increases at T1 after 5 sessions of treatment, and it disappears at T2. It reappears at T3, 10 days after the treatment, substantially unchanged in comparison to that found before the treatment. The mass score was 1 before the treatment. The mass scores was 1 before the treatment. Mass score of 1 means very mild spasticity, and it begins 0, indicating no spasticity in the subsequent evaluation. The ability to perform voluntary wrist movements of flexion extension without co-contraction was present before the treatment and so remains in the subsequent control. So these findings are encouraging. They suggest that the use of the robotic hand in a clinical context, this is very important, in a clinical context of high risk of development of spasticity and associated signs, did not cause any worsening of spasticity, nor induce the onset of co-contraction. In these 2 patients, without the robotic hand, we would have carefully avoided grasping objects with the affected hand. Instead, with the robotic hand, we did it, and we did not found any worsening of spasticity. At March, just at the beginning of spring, our plans and hope were to reproduce very quickly these findings in at least 5-6 subjects. Then the Neurorehabilitation Clinic was transformed overnight in the Centro Covid San Martino, so we looked after a COVID patient for 2 months. It was a very hard, but also very rewarding experience. Now things have changed a lot, fortunately. We have reopened our unit and are starting to experiment again with robotic hand. This data will be confirmed. The robotic hand will allow us to perform grasping tasks in the patients at high risk of developing the positive phenomena. It will be interesting to evaluate the beneficial effects that this possibility will bring to the patients. Thanks for your attention.
Thank you very much, Carlo, for your talk. And so now Paolo will be happy to take some questions. And please, Andrea, go.
Thank you, very nice, Carlo. So just wondering about, and looking forward to your insight, the trade-off between adaptive and maladaptive plasticity, and the rationale of using the robot hand. So if I understand correctly, essentially, those 2 patients you presented had quite some residual distal functionality. They were able to do flexion extension of the wrist. So your concern was mainly to prevent maladaptive plasticity. But I wonder if you have patients with where maybe the major therapeutic goal would that be of regaining sort of grasping capabilities. Would not that sort of require a different approach? In particular, I mean, here essentially what the robot hand was used mainly to train, exercise extension of the fingers, but in a more functional context that will not be enough, wouldn't it be?
Okay. Thanks for the very interesting question. I think that the overt movements, the grasping movements, is more effective in rehabilitation. But in some cases, we have to avoid these movements because we do not want to increase the excitability of the alpha motor neurons. Do you hear me? Yeah. Yeah. Okay. We do want to increase the excitability of the alpha motor neurons, but we do not increase the excitability of the alpha motor neurons only of the flexor muscles, because in the extensor muscles, the positive phenomena are very rare. So at the level of the wrist flexor and the wrist fingers, we do not have this problem. So as far as the flexor muscles are involved, in these kinds of patients, usually we tried to increase the plastic changes that act at a supraspinal level using motor imagery and using action observation. Without the overt movement, we do not activate the alpha motor neurons. However, these strategies are probably less effective than the real movement. Using the robotic hand, we use the patients perform the finalistic movements with grasping and manipulating objects with the extensor muscles, and for the extensor muscle, we stimulate both the plastic changes at the supraspinal levels and at the spinal level. As far as the flexor muscles are involved with this system, we stimulate only the plastic changes at the supraspinal level without modifying the excitability of the alpha motor neurons. So in my mind, this method is the more complete method to exploit all the strategies that we have to increase the plastic changes in the brain without increasing the excitability of the alpha motor neurons, only for the flexor muscle. I hope that I have answered to your question.
Yeah, thanks, quite interesting. But there was maybe offline more discussion.
Thanks, Andrea, for your question. Thanks, Carlo. We have a question from YouTube. I'll read it. So, thanks, Carlo, for the very nice talk. Do you think that it would be good to associate a kind of FES therapy with the SHX protocol? Which would be the possible advantages, disadvantages, if any?
Yes, in the future, this could be an important thing to do, but I prefer to go steps by step, and this first step is to be sure that the device can be used in the subacute stage without negative effect on the positive phenomena. But in the future, it would be very important to check, obviously.
Okay, thank you very much. Any more questions? Antonio, please. Antonio, your mic is off.
Yeah, sorry. If there are no other questions, I might add a comment to Andrea's question. The idea of the soft hand X is to provide a hand that moves under control of the patient, and the control of the patients can be taken from different sides and in different ways, and that should depend on the type of patients that you are treating. So our basic idea was to make this available to clinicians to decide. So we have also tried to use the hand in other configurations, for instance, with a control that comes from EMG for patients that have a more impaired control of the original arm, even in some cases with contralateral arm or orbital controls, or even non-physiologic pathways. But I think the real merit of Carlo, and I'm very happy to acknowledge, is this idea of using the hand in this way that is completely original, that is basically reversing the normal mode. Instead of using it for closing, it's for opening. And for that class of patients, I think it's very promising. So that is, in general, probably other patients you might want to use other controls.
Yeah, no.
Now, can I say it will be very interesting to use transcranial magnetic stimulation in healthy subjects who are using this hand in such a way of activation, to see if the excitability, the cortical excitability of the flexor muscles increases during the task, and using also the recording of the stretch reflex, the H reflex, to be sure that we can induce an excitability of the plastical mechanism, the supraspinal mechanism, without producing an increase of the spinal mechanism. So in healthy subject, using this, using the robotic hand with this in this modality, it would be very important to see the changes at the cortical level and the change at the spinal level using TMS and the H reflex to support our idea.
Thank you, Carlo, and thank you for the interesting discussion. We can move to the second speaker, Professor Andrea D'Avella from University of Messina, that will speak about muscle synergies for human motor control. So thank you very much, Andrea, for being here, and please, I'll be very happy to leave you the stage.
Thank you. Can you see my slides, hear my voice?
Yes, okay. Go ahead.
So, thank you. First of all, really, I would like to thank Matteo Bianchi, Paolo Salaris, and Antonio Bicchi for organizing this meeting, which is very exciting, and for inviting me here. And I'm really glad to be able to interact, or maybe I should say to jam with the roboticists here, because I do believe that interaction between neuroscience and robotics may be beneficial for both fields. Even if, as Paul Verschuer yesterday pointed out nicely, human brains and body are a product of evolution, while robots are really human artifact engineering sort of feats. But both systems, they face the same challenge, the challenge of controlling articulated bodies with many degrees of freedom. So today I would like to provide a neuroscientific perspective of how this challenge can be met. And in neurophysiology, neuroanatomy, and behavioral studies for decades, almost centuries now, have provided a wealth of information on how the human brain controls the body. However, I believe what is still missing is an understanding of the functional organization of this system. So we may know a lot of the ingredients in Marian terms at the implementation level, we understand the computation, but what is really the functional architecture? So today I will try to sort of convince you that a simple yet quantitative model for the generation of motor commands, that is the combination of muscle synergies, may really be helpful to understand better human motor control and possibly to provide a new inspiration for the design of robotic controllers. So today we'll briefly present two examples of how the identification of muscle synergies from muscle patterns recorded during motor task may provide insight in the motor control strategies. And then I also will show how using a little bit like Carlo's experiment was doing in a different context, myoelectric control using EMG signal and also virtual reality in this case allows to test a prediction of a synergistic organization of motor control and also to investigate this more recent ongoing work inter-individual differences in learning abilities. And finally, I will close by showing how this approach may also lead to some novel approaches for neurorehabilitation. So I would say this is not surprising to roboticists if I say that motor control is challenging. These are some excerpts from a few years ago. You're all aware of the DARPA Robotic Challenge. Amazing sort of capabilities, but the failure really indicate how hard it is to control. Even if you take a very simple everyday movement like reaching and grasping for an object, we can use this to really analyze the simple basic computational requirements for controlling a multi-articulated limb. That is essentially that of implementing in neuroscience, we call it sensory motor transformation, which is essentially a control policy. Information about the target, the state of the limb has to be mapped into motor commands, movement. So goals, limb state into actuators, muscle activation. However, the problem is clearly what is inside, how is this control policy implemented? And not surprisingly, one can say, especially in these days of sort of resurgence of neural network as universal approximators, at the end, also the human brain is a large, here just a cartoon of a feed-forward neural network, but is a large recurrent neural network. So this can, of course, is capable of learning any complex mapping, any complex sensory motor transformation. However, biological plausibility of such a mechanism is low, and there are a number of issues with this sort of conceptual approach. First of all, it is true that you can learn mapping, but as a sort of AI, current AI shows, you need a large number of examples, a large number of training trials. And we know that biological systems are can acquire skills, or either they have it genetically somehow encoded, or can acquire it very quickly. And also, if you think that you have a very flexible mapping, it might be that you can learn one specific mapping, but you have to store additional mapping. So this might lead to a problem. Let's see if I can take this. Yes, okay. This can lead to a problem of storing different transformation, each one as a separate, if you want to look up, table. Other approaches, optimal approaches, can sort of describe the dynamics of this complex neural network as implementing computations. So there could be like optimal control computations. However, also these approaches are problematic from a biological point of view because it's not clear how the sort of knowledge that has to be built in this optimal computation is acquired by the network. Then, since almost 20 years, an old concept of muscle synergy has been revived with the idea that it may provide a biological plausible solution to the problem of control and simplifying control. And let me illustrate this with a very simple cartoon. If you have something that to be controlled has a number of sort of variable degrees of freedom, here's in the cartoon are independent wheels of a vehicle, maybe for most tasks, it's not necessary to have that level of independence. You can coordinate some degrees of freedom, coordinate two wheels, remove some degrees of freedom at all. And the same way, human body contains hundreds of muscles. So for many movements, they may be coordinated in group of muscles, and they may be sufficient to achieve adequate control. So again, in this cartoon level, this leads to the idea, to the hypothesis that essentially within this neural network that we know implements this as a functional architecture for complementing a control policy, there might be some modules, some elements that somehow contains enough structure in there, for example, diverging projection to the actuators, such that all computation can be learned and control can be achieved by reducing the effective number of degrees of freedom of variables that have to be set. So a modular organization may somehow simplify the learning and the control by storing knowledge that can be reused across conditions, and thus reducing the dimensionality really of the learning problem of the control problem. So this is the hypothesis that I would like to sort of set up today, that is essentially these at the level of the biological human actuator muscles are really coordinated recruitment of a group of muscle synergies that may be the key architectural element that may simplify control and make it feasible and flexible. And this, of course, requires, though, some assumption that is the small number of elements of synergies may be sufficient for generating useful controls, and this can occur if the synergies have a specific structure. So the structure of the synergies have to capture some regularities in the commands that are used for different conditions. Otherwise, we will not have much flexibilities. So I would say that the notion of synergy, muscle synergy, which has different meanings, for example, in neurorehabilitation, typically is a negative sort of lack of independence in the control of muscles. But in this context, the notion of muscle synergies, and this work started in Emilio Bizzi lab 20 years ago, essentially, can be defined in a simple but quantitative way. That is, muscle synergy is a coordinated recruitment of a group of muscles with specific features in this activation. It can be at the spatial, the temporal, the spatiotemporal level. That is some relationship between the activation of different muscles or the waveform in time, or both. But the key also ingredient of this simple model is that if you have a small number of these synergies, they can be flexibly combined. So the flexibility is achieved not by adjusting the individual degrees of freedom, but by combining these building blocks, these modules. Now, the simple example can be illustrated looking at what we call spatial or time invariant synergies. Consider simply 5 muscles. If you have 5 muscles, so each synergy here represented with this set of horizontal bars with the same color represent a relative level of activation of a group of muscles. So this first red synergy will have muscle 1 and 3 mostly active, whereas 2 and 4 and so on and so forth. So the point again is that we can hypothesize that the nervous system generates motor command by scaling these patterns. So there can be some activation coefficient here illustrated with the C. So the same ratio of activity of different masses is preserved if I scale only one, but flexibility comes from combining with different combination coefficient different synergies. And of course, if this combination coefficient is time varying, one can obtain different time varying patterns. Now, this model can be extended also in the temporal dimension or the spatial temporal dimension. But for brief, for reason of time, I will just focus today on these spatial synergies. Now, the question is, this is a model. How can we actually identify this model? And again, a very simple example to illustrate the approach that has been taken, again, since 20 years. Now, we're looking at muscle activation as sort of points in a muscle activation space. And for simplicity, I represent just a 3-dimensional three-dimensional space. I mean, this point in a three-dimensional space is one observation, can be one-time sample or some average activity in a specific movement. Now imagine that you record muscle patterns across a variety of movement or condition, you observe something like this. Essentially, you can see here there is a clear one-dimensional manifold, in this case linear manifold, that characterizes all these different samples instances. That would be absolutely, I think, acceptable, reasonable to infer that there is a single cause of this relationship. That is, muscles are coordinated, activated with fixed activation balances. But similarly, this would be quite inflexible, the model, though. You can think that if you now observe not just a single one-dimensional manifold, but this in three-dimensional space, a two-dimensional manifold, you can infer that there is a combination on not just one, but two synergies. So essentially, the problem identification is simply a problem of dimensionality reduction. Can we describe motor commands across a variety of conditions simply as generated by combination of a small number of building blocks of modules? And this approach has been taken starting from the work of Matt Tresh in Bizzi lab 20 years ago, looking at frog withdrawal reflexes, and with my work in the same lab, in my PhD, looking at more complex natural behavior in intact frogs. These were experiments done in spinalized frogs, where we develop a time-varying or spatiotemporal model to account for the more complex spatiotemporal features of these muscle patterns. But in locomotion, Yuri Vanenko, Francesco Lacquaniti at Santa Lucia, in postural control, Lina Ting, and also work that we did when I moved back to Italy, Santa Lucia Foundation, looking at muscle pattern enriching, again with the spatiotemporal models. To illustrate just what is the sort of possible insights that we can gain by looking at this sort of decomposition of muscle pattern, let me take a simple case of generating forces isometrically at the hand. So we had experiments with subjects that could see feedback of the force applied as a motion of a cursor, but there is an isometric condition. There is no movement, just the force is recorded by a six-axis force torque transducer, and just the force component is shown as a displacement of the cursor. And we ask subject to do a reaching movement, essentially to reach for a particular target in different direction, for example, on the plane. And of course, we can record the EMGs, and we see direction tune activity depending on the direction of the target. It can be in space, in 2D and 3D. Now, using the dimensionality reduction, in particular, because muscles are non-negative in muscle can only essentially pull, or motor neurons can only increase their firing rates. A standard nowadays approach to decomposing the dimensionality of this muscle pattern is using non-negative matrix factorization. And this is a result of this algorithm, essentially 4 different spatial synergies, each one representing a particular balance of activation of group of muscles. How these synergies are sort of combined to reconstruct EMGs. These are now the time-varying activities for 8 different directions in the plane of over about 15 muscles. As you can see here is when the cursor reaches the target, the dotted line. And now we can essentially, as I showed in the cartoon model before, the simple model, have each synergy is activated by a time-varying coefficient, and the red line here is the reconstruction of this muscle pattern. As you can see, with 4 synergy, we get a very good reconstruction. But maybe more interestingly, if we now see the directional tuning of each of the synergy, we can see that so we are plotting essentially this average activity over time of each of the 4 synergies, that again color-coded in a polar plot. So the directional target and the radial distance is the level of activation of each synergy. You see that these synergies have a simple, almost cosine tuning. So this means essentially that by organizing synergy, many muscles can be recruited with a simple, very simple rule. Essentially, in summary, the combination of a small number of synergy can explain organization of complex also motor muscle patterns, for example, for generating multidirectional forces at the hand. But a simple rule emerges by looking at this approach that is enough to modulate in amplitude with, for example, cosine tuning, the recruitment of 4 synergies to generate all these patterns. Another example, second example I want to briefly present today is in a different context, that of locomotion. This work done at Santa Lucia by Yuri Vanenko, Francesco Lacquaniti, others, and myself, essentially trying to address actually the question that goes beyond the control, but that of the development of the motor skills. So we know that within a 1-year life, typically infant is able to acquire independent locomotion, but is this an inborn capability or requires actually learning? Is something that has to be practiced by trial and error to get the solution. This is a general problem question in development. Now, Nadia Dominici in particular approached this by recording EMGs in neonates. So these are 2 to 7 olds newborns. And as you can see, the newborns, they show this stepping reflex. If the weight, of course, is supported, the neonate will actually flex and extend the leg. That essentially mimics quite the normal sort of gait cycle. Of course, there is no weight support and no propulsion. If you look bilaterally record the EMGs in 2 neonates, you see this alternation of flexion and extension. Here, graze stance and swing in the white 2 cycles are represented. As you can see, neonates have this sort of modulation, almost sinusoidal modulation in time of the activity. If we compare to the pattern of the adults and the same muscles, adults have much more phasic activity, shorter burst with a more distributed and complex temporal structure. But then the composition of this, if you take average, bilateral, not only neonates, adults, but also at the intermediate stages of the development of the walking capabilities, one can use, again, a non-negative matrix factorization to decompose this waveform activation. And here are the temporal components, and here are the weights or the spatial synergies. But in this approach, we focus really on the temporal components of this activation. So the interesting observation here is that in the neonates, as we saw in this simple sort of simpler temporal structure, almost sort of alternating, these EMG patterns can be captured by 2 components, 2 modules that are bilateral, that are representing sort of, if you want, a swing and stance. But as soon as infants start to learn to walk, they show additional 2 components, and these 2 components are preserved, even if they are refined, especially in their narrow sort of peaks in the adults. So it's really the answer to the question also can be look at comparing different species, vertebrate species. Again, in neonates, you have 2 simple components, so some sort of primitive in terms of developmental sense, but also primitive in the phylogenetic sense, because most of the vertebrates have 4 components that resemble those of the toddlers, that are broader in the activation. Only humans, maybe because of their specific adaptation to plantigrade locomotion, they have narrower activation. So in some, 2 basic patterns, 2 muscle synergies, if you want, in the neonates are not are inborn, but they are not just what determines the walking capability, because the system has to learn, is to augment these 2 patterns with 2 additional patterns in order to achieve functional independent locomotion. And moreover, with development, these patterns may become more sort of specific, more refined. And the similarity across different species suggests there is sort of really a phylogenetic basis for this. Finally, I'd like to address an issue that has been raised with this approach of decomposition. That is, how are we sure this is not just a description, but it's nothing to do with the actual organization of the neuroorganization of the synergies. And the way we approached this about 10 years ago, that of thinking, if we have a model, a descriptive model, we can actually test this model if it is actually a causal model for the behavior we see, by making some intervention. And now, if you think synergies reduce, if you want, the degrees of freedom available for controlling, they maybe simplify control, but also they provide a constraint. So then we can predict that if the system is using synergies, if the nervous system is using synergy, then it may be harder to adapt to a perturbation that requires new synergies or modified synergies than to adapt to perturbation that can be used by recombining existing synergies. Essentially, the intervention we're looking at is the adaptive, the plasticity of the nervous system itself that can be sort of trying to regain capability after a perturbation or learning a new skill. So how to test this prediction of a skill or a perturbation that is not compatible with the synergies? Look at this very simple, again, conceptual example. Imagine you have two link arm with 4 muscles. And now imagine that each muscle, of course, at the end generate a particular force. Now imagine the two muscles, these two flexors, are actually, they form a neurally organized synergies that does produce a force, which is the sum of the two forces in this direction. Now, if you do a tendon transfer, you swap this M1 and M4. Now, these neural organized synergies now become two antagonist muscles whose contribution at the end will cancel. So it means these synergies, after this such intervention, will become completely ineffective. If indeed, if it is neural organized, it will be harder to sort of generate force in this direction because they have to break the synergy organized new synergies. So we did not do any actual virtual sort of surgery on subject, but we used virtual reality, again, isometric force generation, to generate virtual surgeries using malletric control. Essentially, the task is the one described before. The subject has to apply a force and to move a cursor in a reaching task. But by using malletric control, we can actually now control the cursor not directly with the force recorded, use that just for calibration, but with the EMGs. And because we control with the EMGs, we can also sort of remap this activity and simulate a tendon transfer. So the EMG control, if it's isometric, a linear model is a good approximation, so we can map each muscle to a particular force direction in the plane, for example, and then again, using a negative matrix factorization, we can identify synergies, this four in this subject, and associate a force to each of these synergy in the plane again. Then again, we can, because we are using direct mapping through the EMGs, we can remap the force that is simulated. Here on the left, you see the forces associated with each individual muscles after this rotation you saw. And this will also sort of perturb what the force each muscle generates in the virtual reality, but also what synergy generates. And we can do this kind of perturbation, which is essentially rotation in muscle space, both in a compatible way. What it means compatible, that the synergies, even if they are perturbed, they're rotated, they still generate forces in all directions. But we can do also in an incompatible way. That is, we generate another rotation such that now the synergy forces are aligned in a single direction. Then, if the control is control independently each muscle, there will be no difference. In fact, we can calibrate these two perturbations the same amount of change at the level of individual muscles. But if it's using synergies, it would be very hard because not all force directions are reachable. So we run experiments with healthy subject, they're performing baseline EMG control. Then we introduce either a compatible, washout, and incompatible surgery. And what we saw here, the cursor trajectory is essentially in the baseline. Because both conditions, subject can reach, for example, 8 targets in the plane. But when you introduce the surgery, we have large distortion. You can see this is the synergy constrained direction, which is mostly where the subject moves. But even if several hundreds of trial practice, in the compatible, they adapt to the perturbation, not so much in the incompatible case where their targets are never reached. And then when we remove in the washout, they have larger after effects in the compatible condition. So we can assess the performance by looking at the error in the angle initial movement direction of the cursor. You can see individual trials in the subject, there is improvement in the compatible, not so much in the incompatible. If you average across blocks, you see these, and average across subject, you can see clearly there is there's no difference in the first block. The perturbation are calibrated with a similar initial sort of errors, but at the end there is a significant difference. So it's much harder to adapt to incompatible surgeries. This means essentially that these virtual surgeries show that synergies are not really simply a description, because they match through the prediction that is harder to adapt to something that cannot be simply re-expressed by recombining existing synergies, and then will require different adaptive process in order to learn a new combination of muscle pattern that generates the proper muscle pattern. So can actually we learn to adapt to incompatible surgeries if we have more time, more practice, with extended practice? Now we are addressing this question by running the same experiment with incompatible and compatible surgeries, but now in 3 sessions, 3 different days. And what we can see here again, as in the single-day experiment, is that subjects can adapt not only to the compatible perturbation, but in some cases also at the 3rd day, they reach good performance also after incompatible perturbation. And importantly, though, when we look at this sort of learning of new synergies that has somehow to do with learning new patterns, so that is learning new motor skills, if we look at the average behavior across subjects, we had 8 and 9 subjects. In the first day, again, as before, we have no improvement in performance percent unsuccessful trials for incompatible, whereas there was an improvement for compatible. But at the third day, it looks like the incompatible two are actually learning. But if we now look at the individual subject, in particular for the incompatible set of subjects, we see that a number of subjects indeed were improving their performance significantly, but other subjects that did not. So it's really there are large inter-individual differences in the learning capabilities. And looking at this challenging task that requires learning new coordination pattern may be a new tool to look at learning of new synergies. So in summary, after an incompatible virtual surgery, there is no improvement in a single session. It's compatible with the idea that learning a new synergies is a slow adaptive process that is distinct from the fast process that is involved in adapting, in motor adaptation, will typically be expressed as recombining existing synergies. And but when we look at longer time scales, it is actually possible to learn. This slow process does occur, but there are also large individual differences. And this in a direction we are actively exploring. I would like, if I have 2 more minutes, don't see here Manolo, I think I would like just to close to a potential application to neurorehabilitation of this muscle synergy approach. Muscle synergy may be used as a diagnostic tool because, in a sense, it may be more sensitive and quantitative indicator of the functional impairments and also the efficacy of rehabilitation treatment, but also can lead to therapeutic approaches that target the specific sort of synergy impairments through potentially specific feedbacks. A few years ago, Vincent Chung in Emilio Bizzi lab showed how after stroke, one can distinguish different changes in the synergistic in the motor organization. There can be, if the impairment not too severe, we can have a preservation of the synergies comparing the paretic and the sound, the effect in the sound arm. But in some cases, we have that the healthy side synergies are merged in a single sort of synergy in the paretic side. Vice versa, there can be some fractionation. So these healthy synergy are fractionated. And this merging is correlated with the severity of the impairment, whereas the fractionation with the duration, so suggesting some maybe compensatory mechanism. Very recently, we have been looking at synergies after a different neurological disorder, cerebellar degeneration, and cerebral patient in a reaching task show much more variable sort of kinematics. But importantly, when we look at the muscle pattern, we are comparing healthy subject with the cerebellar ataxia patient. We see a number of features in the muscle patterns that are sort of distorted. We have sometimes multiple peaks. We have broader activation of the muscle pattern. We have shifting in time of different peaks of the same muscles. So we use now, in this case, spatiotemporal, temporal, in addition to spatial synergy, to characterize the different changes in the features. And what we observe essentially by comparing the reconstruction with spatiotemporal synergies, the spatial synergies were not affected essentially after cerebellar damage, only temporal and especially spatiotemporal synergies. So the reconstruction with the healthy subject synergies was is shown here. For the other healthy subject or cerebral patient was significant difference in the spatiotemporal case. So this suggests essentially that there are changes in the spatiotemporal organization that are induced by the altering of the corticocerebellar loop that is involved in the degeneration. Indeed, one clinical score, the ICAR score, was significantly correlated only with the quality of reconstruction with the spatiotemporal synergies. Now, this idea can be used also for designing new approaches in robot-aided rehabilitation. Current approaches essentially use robots to assist if the subject is not able to move by himself, either endpoint or exoskeleton system. But if the subject is not actively participating, the robot will passively move the hand. Now, if you think about using electric control and synergy, it can lead to some personalized assistance, because one can essentially can take EMG signal to understand the attempt, the motor commands intended on the patient, and then use the information through a synergy-based electric control, and information what are actually the what would have been the physiological activation of muscle synergy that would produce a particular movement, and produce assistive forces only according to the matching essentially of the activation of multiple muscle with the potentially reference synergies that then will be reinforced and trained to regain functional activation. So in sum, muscle synergy provide essentially a model to explain how the complexity of motor control can be tackled by reducing, if you want, the number of the control parameters requires, and by simply mapping goals into muscle activation, synergy combination parameters. For many years, and becoming more and more popular, EMG decomposition shown that a small number of muscle synergies indeed can reconstruct the variety of pattern observed across tasks and different tasks and species. But a more direct test of the synergy hypothesis has come by looking at the prediction that perturbation that is incompatible with synergy will be harder to adapt to than a compatible one. And muscle synergy finally may lead to new approaches in neurorehabilitation, and I would say may inspire also the design of robotic controllers even beyond the neurorehabilitation robotics that has sort of muscle synergies or reduction of the number of parameters as a key ingredient. Thanks for attention. I'd like to thank many collaborators, as Fondazione Santa Lucia, where I'm since 20 years, and also the University of Messina, and for the virtual surgery also Dinesh Pai at the University of British Columbia. Thank you very much.
Thank you, Andrea, for your talk. Any questions for Andrea? Antonio, please go ahead.
Andrea, thank you. Very interesting. Thank you. There is some echo. So the point is very well taken. I mean, this idea that of virtual surgery is really compelling and shows how you adapt to a different set of synergies. I like it very much because it's a clear argument of how things go. I have a technical question, a technical doubt, and some more far-ranging question. So the technical thing that I didn't quite understand, when you do an incompatible surgery, you basically, if I understand, you place all the synergies, the principal components on the same subspace. So you actually cover a subspace of the whole space of possible synergies, right? Still, you move in all directions after training, maybe after 2 or 3 days, you're able to move even in directions that do not belong to the manifold. So how can you get that?
Yeah, so I answer to this so we can go to the more general question. So because robotics is easy to explain, essentially synergies are a subspace in muscle activation space. In order to generate an incompatible surgery, we take a direction in the null space of the EMG to force mapping, because this is a linear mapping, it's a myoelectric control. So we take a direction in the null space and rotate it into essentially in place of one of the synergies that were generating force before. So the way the subject learn to control after incompatible surgery is simply by activating a direction in the null space that was not activated before. So it was not actually part of the intersection between the synergy space and the null space. Okay. What do you call it?
So null space is kind of co-contraction?
Null space is kind of co-contraction, but not all co-contraction is physiological, of course. So typically co-contraction can, as you well know, it can be actively regulated for controlling impedance. We are actually simply, so in theory, the null space is larger even than there is null space also for impedance control in a sense.
Okay.
Right.
Okay.
So, but it's something like that. In fact, we are also investigating how people can learn to co-contract to control, for example, additional degrees of freedom. Yeah.
Okay. Very interesting. So the most part.
But the technical thing is that it's not something they use for reaching. Essentially, they have to associate that to a new control policy.
Okay. Okay. So there is these two words, the muscle synergies and the postural synergies. And we have been working a lot on postural synergies. And I tend to consider the postural synergies as the epiphenomenon of the muscle synergies that are really the motivations. Is there any clear, work that I should read to understand how the muscle synergies map to the postural synergies? There must be a relationship. In a very simple engineering terms, it must be forces towards motions. So double integrator. But is there any study on this mapping?
So, of course, this is a very good question. The issue is really the complexity then of dynamics or kinetics or whatever, because clearly you have a causal mapping, right? Sort of forces, actually, say torques that cause the kinematics. The fact is that this transformation typically is nonlinear. So the question then becomes, the linear combination model may work both in the muscle space and in the postural space, but because the mapping is nonlinear, you can try to have an approximation of it. And there is actually some work that Juan Pablo Carbajal did within a project I was involved, one of the H2020 projects. So I can point you to that, not with muscle, but looking at time-varying torque profiles. How can one approximate essentially any kinematics by recombining sort of muscle pattern generators or time-varying synergies. But clearly, because of nonlinearity is an approximation that you can build of this mapping. We look experimentally at the relationship between muscle synergy and torque synergies, and of course, you can think that for very limited sort of simple task, there could be a direct relationship, but again, the nonlinearities prevent that to be really a simple mapping.
Okay, thank you very much. If you can point us to some of the readings in this
that little simulation work has some inspiration. I'll send it to you, absolutely.
Yeah,
thank you. Years ago. Yeah.
Thanks for the discussion. There are any other questions? If not, I will proceed to read a couple of questions coming from our YouTube followers. So first one, thank you for the interesting talk. Can you comment about the reasons why NMF, I think it stands for non-negative matrix factorization, is preferred to other unsupervised techniques? Have you had any experience with the usage of autoencoders for synergies?
So no, thanks for the question. No, I don't. I have not used autoencoders. I know there is some work. There was actually a paper presented. There is a paper, I think, ICRA this year was using something like autoencoders. There are some ongoing work. NMF actually has been developed actually in Bizzi Lab, not the version that is used now. Before Sebastian Sung published in '99 a Nature paper that became very popular with this multiplicative NMF algorithm. The point is that it matches the constraint, the physiological constraint on non-negativity, and provides a very sort of a robust, we demonstrated that it's, of course, there may be multiple solutions, but the sort of, there is a guarantee that the likelihood of the reconstruction improves with the iterations. So it's a robust algorithm that allows to give a physiological interpretation to the principal components, if you want. Principal components are non-physiological because they are negative, they contain negative components, and they are orthogonal. There is no reason for which the neural network have to organize something that has orthogonality per se. So there's not a principal reason, if not practicality, I would say, and the matching of the proper constraint and assumptions, which are not particularly strong from a statistical point of view. There are no statistical assumptions different, for example, to factor analysis of or ICA. But autoencoders, I think, are promising. I'm not know the details, but I know there is ongoing work. Yeah.
Okay, thank you. I think you have answered perfectly the question. So, second question from YouTube: are synergies pattern the same for all healthy subjects, or are they subject specific? Then if the
no, go ahead.
Because it continues. So if the last, how a rehab therapy can be synergy oriented if we don't know the healthy pattern?
Okay, so very good question. I think this is really, for me, is becoming a central, quite interesting question, because most often in motor control in many disciplines we just average across subjects. You think, oh, let's get the general sort of population behavior. So there are of course similarities, and in particular when we look at, for example, in spatiotemporal synergies across subject, there are a lot of features that are similar across subject, but there are also differences, and these differences may be particularly significant in a patient population. So the point is very well taken. If you are targeting a rehabilitation of specific synergies, you should know what is the adequate solution for a specific individuals. For stroke, the reasonable assumption is that you can try to extract synergies from the non-paretic, the unimpaired side, and use those as references for the impaired side. Otherwise, of course, for other pathologies which you don't have hemiparesis, there could be an open question. What is the reference? Maybe some principle to define according to some maybe anthropometric features or other aspect of the behavior of the specific patient. But still, they should be personalized. That's completely true.
Okay, thank you very much, Andrea, for your talk and for the interesting discussion. Thank you very much. And if there are any other questions, I would like to proceed with the next speaker. So it's my great pleasure to introduce now Lorenzo Masia, full professor at Heidelberg University. And Lorenzo is going to speak about his work on upper limb soft wearable exosuits toward a symbiotic assistive technology. Lorenzo.
All right, let me just try to share the screen if it works. Do you see the presentation now?
Yes, we can see your slides.
Perfect. Okay, thank you very much. So first of all, thanks for the invitation to Professor Antonio Bicchi and all the group from Pisa that I know very well, because actually we had a pod together when I was in Italy. Right now, as introduced, I just joined Heidelberg University 1 year ago, and part of my research deals with soft wearable assistive technology. And this is what I'm going to illustrate right now in this allocated time that I have. So I will talk about soft wearable exosuits, specifically for upper limb, and mainly, you know, the statement towards the symbiotic assistive technology. I would like also to put a question mark, because it's still, you know, an open issue if it's symbiotic or not. I will try to give our last results that we have in this matter. So if we wait a moment. Oh, okay. So it's a bit slow. Part of my lab is called ARIES Lab, that stands for Assistive Robotic and Interactive Exosuit. We do several things. Exosuit is only one part of our research, but we mostly are involved in robotic rehabilitation. That was my primary expertise and background when I started studying during my PhD. And I'm sorry, it's extremely slow. It doesn't change very fast. I don't know why. Okay, so it's absolutely super slow. I will try to understand why. So so there are three main research streams in my field. One is haptics and rehabilitation robotics, intelligent actuation and design. I will talk about human augmentation and soft exosuit. If we start from the genesis of assistive technology, the first experiment in assistive technology was the design from Ralph Mosher from General Electric in 1967. That tried to give the solution for an assistive system that was able actually to lift over 1,000 leaps. And this one was the definition from Ralph Mosher. An exoskeleton is a symbiotic unity with the alacrity of man's information and control system coupled with the machine's power and rapidness. The system was never completed, but it was inspirational for several research. There are several other examples, of course, in exoskeleton from the genesis of exoskeleton from Ralph Masher. Mostly this exoskeleton were used for assistive technology, mainly rehabilitation. Exoskeleton related to wrist rehabilitation, other exoskeleton for lower limb, orthoses that are passive sometimes, systems that are used for military application, and other systems for lower limb or upper limb, especially from Pisa. Over the course of the time, there was a different trend. So we tried to overcome the problems that were related mostly to the rigid exoskeleton that were, of course, affected by inertia and heaviness in terms of motion. And the trend was designing mainly exosuits. An exosuit is mainly something that is made by textile and is actuated with an embedded actuation that can be inflatable system or tendon-driven actuation. And all the sensor systems are embedded itself inside the harness. We have our own prototype that consists in an upper limb exoskeleton or exosuit for hand rehabilitation or assistance and elbow assistance. And it consists in a soft adaptable harness, an embedded actuation that is mainly based on tendon-driven actuation. And everything is extremely lightweight. Also, the controller is embedded. So just let me show you how it works. An exoglove that is one of the part of my research is a system that is based on a tendon-driven actuation. It's quite fast in responding. I will speak about the control later and how it works. And it's easy to on and off in terms of wearing. But this was mainly the concept. Have is something that is extremely lightweight and extremely responsive in terms of control. Of course, the system can be coupled also with an upper limb device that will be mainly the main topic of my presentation, because I will try to illustrate how it works in terms of control. If you want to design an exosuit, mainly there are three pillars: the ergonomics, the actuation, and the control. I'm not going to speak about the ergonomics because, let's say, it's related to a different field, and honestly, also for the sake of time, I would like to concentrate mostly on actuation and control. So if we start about actuation, we use a concept that is called clutchable actuation. Mainly we couple electromechanical actuator to electromechanical clutch. This electromechanical clutch will engage and disengage when the assistance is needed. This means that when it's not engaged, the system results completely transparent to movement, but when it's engaged, the motor actuates the spool that where the cable are wrapped, and then this cable, of course, moves the load that can be, for example, a wrist or a shoulder or an elbow. So this is how the electromechanical clutch works. The system is able to rotate. At one point, when the clutch is not engaged, you can move the system freely. So you can imagine that you can move your hand. But then when the system engages and detect, for example, let's suppose a spike from the electromyography, the system tends to apply, of course, a certain force. We are currently also experiencing some new design by using drone motors that are extremely efficient and they offer a lot of torques. And of course, I mean, this is another new trend in soft wearable exosuit that right now is rising very high. Another example of how to design actuation was how to decrease the number of motors that you need to move user's limb. Consider that for every motor, there's a driver, there's also, you know, a larger battery. What happens if I have one motor that I will call prime mover and different clutches that can engage or disengage, actuating different degrees of freedom, but just using one electromechanical actuator. This one was an interesting work that was done in collaboration with the group of Antonio Bicchi, because Marco Canesi was one of his master students that came to NTU Singapore and spent with me about 6 months. So we worked together, and at the end, we designed the system. Let me show you how it works just briefly. It's a mechanism based on several clutches, electromechanical clutches, and mainly the idea is having one motor that is called prime mover to power two different modules that you will see here, left and right, that corresponds to the left and the right shoulder. The system is extremely compact, And each of this module consists in an assembly of different gears that rotates in different directions. And these clutches actuate and deactuate the passing shaft. So for example, if I want to create a trapezoidal profile, I can engage and disengage the clutch in a very fast sequence and realize this kind of actuation strategy. Let me show you how the system is fast. So if I want, for example, to follow a sinusoidal trajectory, I need to engage and disengage the clutch here very fast between the two wheels. And I will try to follow this trajectory as fast as I can. Consider that an electromechanical clutch has a time of activation of about 50 milliseconds. Of course, you have segmentation of trajectory because the clutch engage and disengage on and off. So let's say electronically. So the system mainly here behind this guy, there's a motor that is rotating at one speed. You can lock this arm in one position and the other arm can move, or they can both move if I engage or disengage the different clutches. Okay, so this one was the idea. Let me go a bit more in details how to control an exosuit. That is still an open issue right now. An exosuit cannot rely on the laws of rigid robotics that were developed for industrial robotics, because mainly you have a lot of non-linearities. When you have a flexible system, you have to deal with especially if you have Bowden cable on tendon-driven transmission, friction, stiction, hysteresis. How can you deal with this kind of things? Well, in order to deal with non-linearities and at the same time results intuitive, you need to decode the human motion intention, compensate for backlash, and compensate for friction at the same time. And the idea is try to sensorize the system as much as you can. Here, for example, we are not using biosignals, so no electromyography, nothing, but just a force sensor and a flex sensor that will give us the rotation of the elbow and the tension of the tendon that is trying to actuate the elbow of the human arm. And the first example that we designed was called, I call controller one, a hierarchical cascade controller. Why hierarchical? Because mainly there's a hierarchy between the low level that tends to compensate mainly friction and drives the electromechanical actuation, a middle level that compensates for backlash and hysteresis, and the top level that mainly consists in understanding what is the dynamic of the human arm and transmit the force and the assistance by means of an admittance control. Yes. So let me just go for the assistive control, that is the upper part. Mainly we rely on a sort of simple equation to understand how two tendons in configuration of agonist and antagonist actuation can apply torque with respect to the human arm. If we start for the assistive torque and we go to the human torque estimator, we need a very simple model of the human arm, mainly that relates the torque that the gravity force apply at the elbow level. Everything is then translated into an admittance control that by the detection of the force that this very simple model deliver, the admittance control output kinematics that then can be compensated or must be compensated at the level of backlash. And we are not going to use anything new because we use what is called Bock and Venn model that mainly is something extremely used, for example, in surgical robotics, especially if you have endoscopic systems. And for what concerns instead the friction compensation, we use what is called the Lugre model. By using this different approach that is mainly organized in layers, what we can have is a system that is, I would say, responsive in an acceptable way. Because as you see, here is there's a platform, a very simple user interface. You need to follow the signal of this user interface. And between the application, the same movement without exosuit and with the exosuit, the track of the EMG is very different. Here on this other side, you see mainly the torque that is computed in real time by using this kind of model. So what we can say, well, first of all, there's a quite a significant reduction in muscular activity, because despite we didn't use electromyographic system to drive exosuit, we use the electromyographic system in order to understand if there was a decrease in terms of muscular activity. And here you see different curves mediated all over the subject that we tested. And its statistical significance, this reduction in muscular activity. If we consider instead how the system behaves for high speed and low speed. So you can see, for example, that for low speed, the reduction in muscular activity is quite obvious with respect to high speed. But if you look at what happened in terms of control effort, at low speed, the control effort of the system is higher. While at high speed, the control effort, and this means that the level of assistance of the system is lower. And what does it mean? Well, mainly it means that the system detects if the subject is able to move or not, and then, depending if you are moving at a certain speed or not, increase or decrease the activity of the assistance. So helping, for example, in case of a subject affected by impaired an upper limb, in moving the elbow against the gravity. In terms of compensation respect, the desired command, that is the one actuated and that is the one obtained by the model for friction compensation and Bowden cable hysteresis, we have that the desire and the measured trajectory in terms of the elbow and the motor is quite decent. So there are no much errors. So fits very well what happens in terms of compensation. And then another thing is, despite we do not use electromyographic signal, that is this black line, the torque that is applied by the system resembles, even if here is scaled down respect to the electromyography, resembles the electromyographic signal itself. So it means that the system can be used even if we are not considering biosignal, but still we have a resembling waveform of the assistance respect to the muscular activity. Of course, we step up and we try to design a controller that is based on a dynamic arm model in order to compensate for gravity, move in concert with the wearer, and behave in a more transparent way. The system consists mainly in an outer loop that comprised an assistance estimator and an admittance control, an inner velocity loop to the motor to close the velocity directly at the level of the motor, and a positive feedback that tends to compensate in part the dynamic friction inside the Bowden cable. Well, how the system works. So this is, for example, this is the force sensor that detects when you attempt to move and try to respond as much as it can. One thing that we can say is that, of course, if you move very abruptly, you see that there's a sort of delay because the cable slack at one point. And I will discuss later this effect. So we actually set also an experimental protocol. We tested 8 subjects with and without assistance of the exosuit. So the cable was removed when the actuation was not assisting. And then we asked to follow a reference by a graphical user interface. And we experienced, we tested the subject during dynamic task and static task. Let me call a bit about the dynamic task. We tested the system for different velocity, for different amplitude of the movement. And then we wanted to access and understand what happens to the physiological kinematics when you apply this kind of assistance. So if we look, for example, these curves that are the one superimposed by the graphical user interface and the one followed by the exosuit, they resemble, I would say, quite well. If we go, for example, and test for velocity that is very low, average velocity, and high velocity, you see that the powered and unpowered, so with and without the exosuit, the powered system tends to be delayed. So it means that when I want to attempt very fast, the system is not able to entirely follow the dynamics of my trajectory. This is more accentuated, if you see, it's more visible when you increase the velocity. Without the exosuit, I can almost follow the desired trajectory imposed by the graphical user interface, but with the exosuit, honestly, the assistance of the exosuit delayed a bit. This is clearly visible here, of course, that there's a trend that is a decreasing trend in terms of assistance as function of increasing velocity, and also in terms of smoothness. So it means that for very high velocity, the smoothness of my free motion is much better than the one with the exosuit. What about change in biological torque? Am I really augmenting the action of a subject? Well, of course, there's a change in biological torque. If you look, for example, this curve's total of torque is the gray, the dark is exosuit, and the biological torque. When you pass from a low velocity, medium velocity, and high velocity, the biological torque, so the torque that the human should input inside at the interaction with the exosuit, increase. And this is clearly visible also because you see that there's a trend that increase for low velocity to high velocity. What about change in activity of biceps and triceps muscles? This is something also that we saw, of course. So if we consider, for example, the biceps, that is the muscle that is more interested and involved in the motion, you see that powered and unpowered, during unpowered exercise and motion, the activity of the MG is much higher respect to the powered version of the exercise. And here you can see also the trend with the increase of reduction in EMG with the biceps. So it means mainly that the biceps is increasing the activity when is requested a higher velocity. What about the fatigue, the muscular fatigue? And this is important for application like, for example, industrial application, if in the future, near or far, we want to use this kind of things. The muscular fatigue, of course, depends also on the frequency on the EMG. If we consider the average rectified value and the median frequency, that are the main indicators for the muscular fatigue, you see that for respect to the unpowered condition, muscular fatigue tends to be postponed. This means that the use of the exosuit actually postponed the initiation of muscular fatigue, and in certain terms of, let's say, muscular metabolism can improve the action. So the main message is wearing the exosuit delay the onset of fatigue, reduce biological torque, but reduce also muscular effort. What is the disadvantage? Well, we see that there are disadvantages in terms of connection, kinematic connection, and symbiosis between the dynamic of the exosuit and the dynamic of the human heart. How can we obviate? Can we really try to create a controller and an exosuit that merge together, provide a symbiotic interaction with the user? The idea came when I spent almost a year at the University of Twente, and there was a sort of a nice astral conjunction between the presence there, because there was Nicola Lotti, that was a student of Vittorio Sanguinetti, that is an expert in haptics and robotic rehabilitation. There was Massimo Sartori at the University of Twente, that is probably the leading person in musculoskeletal modeling for assistive technology. There was me, that I'm not expert, of course, as much as they are, but I can do something in exosuit, and my student Michele Xiloyannis, that is now in charge as a postdoc at ETH. So we put together our notion of exosuits, robotic control, and musculoskeletal modeling, and we try to create something for a wearable exosuit that is more symbiotic, using what is called a myoelectric control based on a myoprocessor. And let me just change. Why a myoprocessor? So the idea was, can we use a myoprocessing technique, so an extrapolation of the force from model of the human muscles, in order to put in parallel to the action of the musculoskeletal system, the natural musculoskeletal system, something that can be assumed to be a nasomuscles, and see how the system behaves? Well, we make some experiment. We try to compensate, we just implemented the control to try to compensate intrinsic dynamic and external mechanical loads that are varying this time, and try to adapt the assistance to different movement velocity and load condition. So the myoprocessing module techniques comprises mainly 4 blocks: an activation dynamics, a musculotendon unit kinematics, musculotendon units dynamics, and of course a torque computation that is based on a modeling of the human arm. If we consider the activation dynamics, I'm not going to go into details, but mainly we use dynamics and equation from Lloyd and Bézier, from EMG to activation filter and EMG to activation relationship. Then we use also from Lloyd and Tellen a model of the muscle that comprise the force-length relationship and the force velocity, the parallel contribution also of the muscular fibers, and we consider also the muscular activation. And then we put everything in an OpenSim model in order to scale the musculoskeletal model of the musculoskeletal anthropometric parts of each subject into an OpenSim model in order to compute the torque from the model itself. Okay, there's a process of calibration. And then we repeated the same tracking task that I showed you before, different velocity and different load condition. So this is an idea of how the system works in real time. Here you see the electromyography, these are the force of the different muscles that we were considering. We were considering several muscles, so mainly triceps, biceps, and brachioradialis muscles. And here is the online real-time computation torque at the elbow. And the system reacts quite fast. So what we can say? Well, first of all, we can say that if we extract the inverse dynamic here from the OpenSim model, and we correlate this inverse dynamic to the output in terms of torque with the EMG models that we implemented, the waveform is quite resemble quite well the OpenSim models. Another thing that is important is that we have a delay between the electromechanical delay between the actuation, the biological actuation of the muscles and the computation of the torque that is about 45 milliseconds. So the system, in terms of computational capacity, is extremely fast. Oh, these 45 milliseconds are not considering also the actuation. But later I will show that also in terms of actuating force, the system reacts quite well. In terms of powered and unpowered reference and reference confrontation, well, you see that mainly if I try to follow this kind of curve that is the desired curve, even if I change between 0 kilograms, so free motion, and 2 kilograms, I succeed in following this reference motion quite well with the exosuit. Plus, let's consider this kind of aspect that is quite important. If I move, so these are 3 movements, up and down, up and down, up and down with my elbow. And I put 0 kilograms, 1 kilograms, and 2 kilograms. You see that in the unpowered condition, that is the gray line, so it's the activity of the EMG for the biceps. Of course, between 0 kilograms, 1 kilograms, and 2 kilograms, I have an increase. Okay, but something that is happening is that with this kind of model, increase also the output from the controller. And this is something that is extremely interesting because it means that the controller is slightly adapting without tuning any gains. The higher is the electromechanical, electromyographic activity, and the higher seems to be also, of course, in a nonlinear way, because otherwise they will sum up, the actuation and the assistance from the device. So the conclusion is that this microprocessor is quite reliable in terms of estimate the elbow torque. For sure, is extremely accurate and responds seems to respond much better with respect to the other dynamic arm model that was not using biometric feedback. And it results very much transparent in terms of human arm control. Now the question is, who's better for this kind of task of elbow lifting? The model-based myoelectric control, the myoprocessor, or the dynamic-based controller? So what is the better solution? We run more or less the same approach, but just implementing a controller that is able to switch between dynamic model and myoprocessing technique. So here with no EMG, here with EMG. So it's just controller 2 and microprocessor that I just presented. And then we tested them on different tasks. What kind of task? Well, we redesign our system with the 2 EMG signal here, an off-board actuation that has much more power and higher bandwidth with respect to the previous one. And then we tested the 3 different tasks. Pick and place, that is very accurate task. So just picking a different object and placing the object in specific location. A very dynamic task that is throwing and catching a ball between 2 operator, one that is using the exosuit and one that is not using. And also we want to check how the system behaves in terms of rejection of external disturbances. So we let fall a ball that was 1 kilogram and the subject was blindfolded, so was not able to understand what was happening and when the throw was left falling. So let's see the results. What about the step response? Let me start with happens when the step response. So if I consider, for example, the two-step response, stop. Okay. Now you should see. So I left the falling, and of course the two controller respond in a different way. Okay. So what is this different way of responding? Well, of course, what I want to see is when the system intervene and try to reject the disturbance. Here we find quite an interesting results that, of course, the system that is based on myoprocessing technique here responds much faster than the system that is using instead the dynamic arm model. And the difference is significant. Okay, so we have difference not only in the response time, but also in the settling time. And the myoprocessing system, the myoprocessor, stabilized the arm in a much faster way respect to the dynamic arm. What about the pick and place task? For the pick and place task, also here, if we consider the torque that is exerted in absence of exosuit that we extrapolated for the OpenSim model, you see that between 200 grams, 500 grams, and 1,000 grams, this gray line tends to increase because, of course, I have a higher load. What about the dynamic arm? This blue line, yes, tends to increase, but not significantly. But what about the myoprocessing? The myoprocessor? Well, the myoprocessor tends to increase in a way that goes almost in the same way as the free motion, so without the assistance. And this is something that you can see also from these curves here at the right, where increasing the load, the myoprocessor, that is the red one, is going with the same positive trend that the torque that is computed during free motion. The same thing, this is not the same instead for the dynamic arm model in absence of EMG feedback, because the curve seems to be flat, so the assistance seems to be more or less the same. What about the catch and throw, unimanual and bimanual? So as you can see, the system is quite fast in both the controllers. Okay, so we are actually, for the bimanual, the ball was about 2 kilograms or even more. This red ball is about 1 kilogram. They are medical balls, so they're right in terms of weight. Now I don't remember. Let me show you what happens. So instead of looking this plot that actually is giving you the dynamic arm and the myoprocessor power during this launch of the ball in a unimanual task, let's see, for example, what happened in terms of work and energy that is consumed without assistance. This is what you consume without the ball, without the exosuit. This is what you consume here in terms of dynamic arm. So you see that the total amount of power, that is this one, is not comparable with the one that you succeed in delivered during free motion. And also the effort of the dynamic arm model is much lower than the one of the human arm. So it means that when you have the dynamic arm model during this dynamic task, the human arm should push more than the exosuit. When you have the exosuit with the myoprocessing system on board, well, mainly the two powers in free motion and with the myoprocessor on are similar, and the exosuit push even more in terms of power respect to the human. So it means that actually for this dynamic task, the myoprocessing system, the control that is based on myoprocessor is much more responsive and is much more assisting also. Another thing that we can consider also, what happened when you throw the ball. Well, here you can clearly see how much is the delay respect of the electromyographic signal of the dynamic arm and the exosuit, while the exosuit with the myoprocessing. While the myoprocessor seems to resemble the waveform of the electromyographic signal, this one is not only scaled down, but it's also delayed. And in fact, you can see here that that the delay in terms of activation, also in unimanual and bimanual tasks, are extremely different between the two controllers. So the conclusion of the comparison is the microprocessor performs better in dynamic tasks with rather than the dynamic controller. It adapts in real time with no retuning of the gains. This is quite important. So once I calibrate the model works on that subject independently on the load, and it outperforms in terms of the dynamic harmonic controller in time response and physiological kinematics. So it seems to be more symbiotic. But the dynamic arm model, on the other side, it does not need any calibration and fitting. So you just take the measure of the subject, tune the controller once, and it's fine, and it will assist. It is based only on anthropometric values that are readily extractable from the arm of the subject, and does not need any biosignal detection, so has no signal degradation that especially if you use electromyography for a long time, and the electrical impedance at the interface between the electrons and the skin change, of course, I mean, you can have a signal that is different from the one that you have at the beginning during the calibration. This was my last slide. I would like to I would like to thank the lab of my university here with all the groups, Nicola Lotti especially, that is the person in charge for this kind of stream of my research. The ETH Zurich with Michele, that was my ex-PhD student, now is with Robert Riener, Domenico Chiaradia and Antonio Frisoli, Nicola Vitiello, with whom I'm starting quite a nice collaboration in passive-active soft wearable system, and of course Massimo Sartori, with whom I had the luck to work in those months that I was in Twente, and it was very inspirational in terms of new control strategy for soft wearable exosuit. Thank you very much. I finish here my presentation.
Thank you, Lorenzo, for your presentation. Very, very interesting. Any question for Lorenzo? Okay, so meanwhile, okay, please, Andrea, go ahead.
As promised, no? I have done. It's okay. For a matter of time, the interpretation of data question offline. No, instead not the nasty question, no, the good question. No, I think that I see a great opportunity of using I'm trying to tie with my talk, right? That is using the microprocessor not for assistance, but for creating perturbations. Essentially, yes, with the reasonable delays, you could still think that you could be performing these tendon transfer surgeries that are described in the isometric setup in actually during unconstrained movement. Essentially, you could simulate a virtual muscle that sort of driven by EMG activation that produces a force as if it were a different muscle. Are you planning to do so?
Honestly, not, because someone else is doing, so I don't want to copy anyone. But I know that, you know, this was an idea that you had in mind, that you had also, I think, during a discussion with Vittorio, is extremely interesting. Let's say that the approach is very much on neuroscience, while I am much more into, let's say, assistive and augmentation. But definitely, I mean, you can use this kind of approach to create perturbation. The only problem that I see is just try to find the right tuning between the dynamics that is communicated by the model-based controller to the, for example, the dynamic of the haptic interface that you want to use, because of course there would be a dynamic and all the delay that you have to consider in terms of compensation. Then it depends, of course, what you want to use. If it's one of this end effector manipulandum, the systems are quite rigid, and they, you know, and you do not start with any kind of problems in terms of compensation of non-linearities and what is with them. Yeah. But of course, there's space for a discussion, that's for sure.
Thanks, Lorenzo. We have a question from a YouTube follower. Thanks, Prof. Masia, for this talk. I'd like to ask you if you tested the microprocessor model in different muscle conditions. For example, like after incoming of fatigue, does it respond the same?
I didn't get. For example, in
like after incoming of fatigue.
Well, we tested on fatigue, but I don't have the data here right now. Yes, and not from different muscles. Right now, we are only tested the elbow. Who tested on different muscle? Of course, is Massimo Sartori, especially for lower limb. For lower limb, Massimo, because I mean, he's probably the person that started and ignited this kind of use of the myoprocessing technique for assistive technology. He used, of course, I mean, for I would say for orthosis on lower limb, that's for sure, with rigid exoskeleton, and also for upper limb in prosthetics. But I don't know if he uses for testing fatigues. We had some data on fatigues, but I didn't show them, you know, for sake of time today.
Yeah, totally, I can understand. Okay, so my very last question, Lorenzo. In one of our recent works, actually, we understood that the fact that an exoskeleton can really regulate the muscle effort is very much related with the fact that there is a control loop from the centroperipheral nervous system. And actually, if you doesn't take into account this control loop, it turns out that the muscle effort is not controllable. It's not really controllable from the exoskeleton. And so my question is, are you planning to use a model of the control loop that the nervous system implements to achieve a task in your future version of your controller? Or
okay, let's say that I love simplicity in the sense that you might for sure adopt something like this, but then if you want to use the system in a clinical setting, what kind of model you are going to use, on how you can adapt your model to the wide range of difference that you have, and non-uniformity across the subjects. And speaking about clinical settings, if you speak about industrial settings, also there, one model works for everyone. How can you retune a model for every user? So it's true that right now, you know, I'm trying to understand how, for example, using a EMG-based driven system to assist motion, but I am still a fan of non-biosignal driven system. So I, you know, based on mechanical design, controller implementation, I'm pretty sure that a system that works without using biosignal, but detects at the interface between the user and the exosuit the interaction, can still support for certain tasks in a very reliable way and in an extremely easy way in terms of computational power. This is what I believe. So if you want to put on the market something that needs to assist motion, you cannot just run calibration, pre-calibration, tuning setting. No, it just should work once the subject put the weight and put the height and put one measure. This is my approach. Okay. So modeling.
May I briefly comment on Manolo's question? I think that my intuition would be the most successful approach is having the user learn the model of the robot, and vice versa. That is maybe what is critical. So I buy the simplicity. If the controller that the robot is implementing is actually sort of transparent enough, not in the sense of mechanical transparent, but can be actually modeled by the user will learn to use it properly. Even if, let's say, a delay, you know, if the delay is very predictable in a sense, the user may be able to learn to integrate the delay that either is by signal or a torque sense. It doesn't matter, because it's the mechanic. So there is the loop of the robot controller that has to be predicted by the user. Yeah.
I mean, we should rely a bit more on the plasticity of the human brain, in the sense that when you buy, for example, let's speak about something that you should you should have it, a new motorbike. You need to learn the dynamic of the system, of the vehicle. And once you learn the dynamic, the symbiosis between your dynamic and the one of the motorbike merged together gives you the ability to go fast. So that's my idea. So a consumable should be something that adapts to a different range of users, but then the user should, develop this kind of symbiosis between the
then
system
the really
itself.
interesting question then is what is easier to learn for a human as the dynamic of the control loop? Right?
No, okay.
Because the easier, the better for the user. It's something that you somehow have some precognition, so you have some prior on how will adapt to your commands, then it will be easier to use.
Okay, thanks for the interesting discussion. We have a very last question for you, Lorenzo. What do you think about the possibility of defining EMG activity reduction goals instead of observing only a posteriori EMG reduction? Do you think it is possible?
Sorry, I was reading this question on YouTube. Can you repeat it? I didn't find the question.
Yeah, the question is, instead of observing only a posteriori EMG reduction, it is possible to set this as a goal of the controller, like, for example, an output to regulate to 0 or something like that, or a performance index to minimize.
But for sure, the thing that this kind of controller that use EMG are on different layers. So if you take the model that extrapolate EMG and then transform to torque, then this torque, the signal torque goes to the low-level controller that is a force controller, an admittance controller, impedance controller. Something that you can say is that, for example, the gains that regulates the assistance should decrease or increase depending on the performance of the subject. That one, is something that you can do. So the EMG, of course, will decrease when I increase the proportional gain of a proportional derivative gain and an impedance controller. Yeah, but then the subject needs to readapt himself or herself to a new dynamic, because the dynamic of the exosuit and the one of the human arm put together is changed. Do you understand what I mean? It's like playing tennis with a racket that is very light, and then they give you a racket that is 10 grams more. You say, but 10 grams is nothing. It depends, because you are moving at very high speed when you play tennis. And of course, the inertial load of 10 grams on a movement of a tennis racket that is several kilometers per hour is perceived by you with something completely new in order to manage the, let's say, the gesture and having an efficient backhand or forehand. The same with the exosuit, even if we are not talking about very high dynamics, but when you change a small gain, then the response of the system will change and your muscular activation will change consequently to perform the same task. So there's a new readaptation.
Thank you. I think you answered comprehensively to the question and the other question. So thank you very much for the discussion. And I think we are ready for the coffee break. And we'll be here again in 15 minutes or so. So thank you very much again, Lorenzo, for your presentation. Very nice and very, very nice discussion.
Thank you. Thank you very much.
Dimmi, are we live? Okay, so welcome everybody to the second part of the day 2 of the Robotics Research Jam session. After the first 3 speakers, 2 from scientific side and 1 from robotics rehabilitation side, we have now Lorenzo Sabattini from University of Modena and Reggio-Emilia that will speak about towards human-friendly multi-robot system.
Okay, thank you very much for the introduction. I'm trying to share the file. Let me see. Okay, I think it's working. So, well, thank you. Good morning to everyone. Thanks very much for the invitation and thanks everybody for being here. I'm Lorenzo Sabattini. I'm Associate Professor at the University of Modena, Reggio Emilia, Italy, and I will tell you something about our work on interaction with multi-robot systems. So how to make a multi-robot system human-friendly. I will tell you a little bit more about what we mean about that with this term. So first of all, let me start with an acknowledgement to my PhD student, Beatrice Capelli, who is the main author of this work. And of course, everything I'm presenting is mainly her work. So I felt like I should acknowledge this in the first slide. So, and well, of course, I mean, I will be happy to answer any question at the end of the presentation, but if you have more questions, then you can write to me or to Beatrice directly in case anyone wants to interact or to exchange information or ideas. So let me motivate a little bit this work. So the topic we are addressing is that of interaction with a multi-robot system. So what do we mean by interaction with a multi-robot system? So multi-robot system in general is a group of robots, let's say, and there is actually a large body of work on control of multi-robot systems, on how to make these robots cooperate among each other, and how to make them essentially behave in an autonomous manner. But you know, once it comes to real-world applications, so several times you cannot really rely on autonomous systems only. So you do need to have interaction with people. So you need to have people in the game, and that's why. So the problem of interaction with a multi-robot system comes in the game. So typically, there is, of course, there were other people considering this problem, and the typical question that is more often asked is how should a person provide an input to a multi-robot system? And so then there is a quite large body of literature on providing and developing methodologies for solving these issues. So for instance, using gestures, using teleoperation system, using speech synthesis, speech recognition, and so on and so forth. However, here we are trying to address a slightly different perspective. So how should the multi-robot system communicate to the user? So the other way around, let's say, the other channel of communication. So why should we be interested in this kind of channel, in this kind of interaction? Well, if we need to share the environment with a robotic system, a multi-robot system in particular, then if I have to do that, I want to be aware of what's going on. And if I am the roboticist who programmed and developed the control law, maybe I'm, let's say, by default aware of what's going on. But if it's a common person who has no expertise in robotics, then it's important that the robotic system communicates and tells the person what's going on, so that the environment can be shared in a convenient manner, both from a task point of view and also from a comfort point of view, so the user can be comfortable. And in particular, this is particularly true when you need to cooperate with these multi-robot systems. So for instance, there is a transportation and the user needs to interact with this system. So it's important to make the user aware of what's going on. So what's a multi-robot system? It's a fairly, let's say, general definition. So in general, you can have a group of robots, so of very different kinds of robots. So in general, things that move in the environment. So it can be manipulators, or it can be mobile robots of different kinds. It can be heterogeneous robots. So, but in general, there are some, let's say, common issues. So the common issue is, well, we have things that move around and we want to understand what's going on. In particular, when it comes to proximal interaction. So what do we mean by proximal interaction? Proximal interaction is when the user and the robot or the multi-robot system share the same environment. So we interact with the robot closely. So it's not an interaction mediated via a teleoperation device, for instance, but it's when we are in the same room and or in the same industrial environment, and we are sharing, so sharing the space, sharing the same space. So in order to ensure that this proximal interaction can happen in an effective manner and in a comfortable manner, then here we are exploiting the concept of legibility. So the concept of legibility in a couple of words means how to ensure that the robot, or in general the system, but in this case the robot, is able to communicate its intention to the user. So a motion pattern is legible if it's understandable by the human operator. So how to perform this kind of communication? Of course, there are different methods. So the communication from the robot to the user, how the robot should communicate its intention to the user. We can use let's say the most common and natural way of thinking about it is by means of explicit cues. So explicit cues, I mean some devices, some structures, some elements that are designed, installed, and controlled explicitly for communication purposes. So we can have LED rings, as we can see in the figure. We can have speech synthesis. We can have some visual cues, some visual representations on the floor, and so on and so forth. The advantage of an explicit communication is that it's typically easy to understand. So if I have an alphabet of symbols and these symbols are represented by LED colors, then it's easy to understand what the robots want to communicate to me. However, there are also disadvantages of this kind of communication. We need to have devices that are there only for communication purposes, and we need to have an alphabet typically. And if we have many robots that try to communicate different things, it can be very difficult for the user to process the information, and it can distract the user from the main task that he or she is carrying on. So that's why we are trying to focus more on implicit communication. So implicit cues means essentially how to define the motion of the robot to implicitly show the intention to the user. So in this is a prototypical example that can be found in the literature. This robot has to grab one of the two bottles in the right hand of the slide. Well, if the robot moves in a straight line, then it's difficult for the user to understand the intention of the robot. If the robot makes a curved path to reach the bottle, then it's easier for the user to understand what's happening. So from a task point of view, grabbing the bottle, the motion is less effective, but at the same time, it helps the user to understand what's going on. So we are trying to exploit this concept in a multi-robot system scenario. So a multi-robot system scenario in which we have multiple robots that are typically cooperating among each other and that in this setting want to provide information to the user. The point is that the robots can be many, so we can have many robots. So we cannot assume that the user is able to process the information coming from each of them. We need to have some aggregate information, because otherwise the user will never be able, cognitively able, to really understand and follow what's going on. So the question that we are asking is it possible to communicate something through the motion pattern of the multi-robot system? So in order to do that, we built let's say a toy experiment, a toy example, in which we have a group of robots that need to reach a goal. And as you can see here in the animation, we have 7 possible goals, the squares that you see all around the robots. And the robots, the group of robots is tasked to reach one of these goals. Well, based on how we define the motion pattern of the multi-robot system, is it possible to communicate to the user what is the goal of the multi-robot system itself before, of course, reaching the goal? So given the state of the system, is it possible for the user to infer the goal of the robot? The goal of the robots, sorry. So by state of the system, in this case, we are let's say aggregating some parameters that define the overall motion of the robots in an aggregate manner. So we are considering essentially different characteristics of the motion pattern and of the forces applied among the robots to make them work cohesively. And based on different characteristics, we are trying to see if these characteristics can influence how the user understands the objective of the multi-robot system. So in particular, we are considering 3 main parameters. So one is the overall trajectory of the center of mass of the robot. So we use a straight line trajectory and a curved trajectory. Then we are considering the dispersion, so how the robots are aggregated and how much they are dispersed. So we see more clearly if it's a group moving together or if they are more spread in the environment. And also we consider the stiffness of the interconnection among them. So by stiffness, we mean how rigidly they are interconnected among each other. So how much the relative positions are constrained, how much they are fixed, and how much they can move, like as if they were connected with a variable stiffness spring, something like this. Well, just to give you some visualization, so these are the different kinds of trajectories that we consider. With the colored lines, you see the motion of each specific robot, and with the bunch of lines, you see the overall motion of the group of robots. And actually, we consider 2 cases, one with only one group of robots with one and only one objective common, and another second example with several groups of robots which could have possibly different objectives. So we try to understand if different kinds of trajectories and different levels of dispersion and of stiffness could influence the ability of the user to understand the objective of the fleet of robots. So the previous pictures were about the different kinds of trajectory. Here we visualize what we mean by stiffness and dispersion. So actually what we are considering is a double integrator system controlled with an artificial potential field. Okay, and this artificial potential field is used to define the relationship among neighboring robots, the repulsive action to avoid collisions among the robots, and an attraction towards the goal. So actually these parameters, the parameters that define the potential field actually define in case of the rest length of the spring, we define the dispersion level, and in case of the gain, we define the level of stiffness of the interconnection itself. So how did we perform the experiments? Of course, I mean, these were our claims. So let's see if these parameters influence the ability of the user to understand. Well, to do that, we made some experiments with different subjects. So using a within subject methodology, and we used as independent variables the three variables that I mentioned already, and as dependent variables the correctness. So is the user able to correctly understand the goal of the multi-robot system, and the response time. How long does the user take to give the correct answer? So here we have some experiments. I hope the video will start soon. Actually, the experiments were done in virtual reality. And so the advantage of virtual reality was that actually we can have the controlled conditions and repeat always the same condition for the different people. And also you can have a wider space than with respect to the space that unfortunately we have in the lab. So actually I tried the video yesterday and it was working very well. Now, of course, it's not working, as always. Let me see if the second video works. Otherwise, you will trust me somehow. Or maybe I can try to share the video in a different manner. I can try to share the video externally. Let me see. Sorry about that. I will share this. Okay, so maybe now you should see the video that I'm sharing. So as you can see, we are using this virtual reality scenario in which in which the user is able to see, of course, in the screen, we see the first person view of the user. And well, the user had in front of her these different colored cubes, and she had to select which of the colored cubes she thought was the goal of the system. Of course, you can see that the robots, based on how we define the interaction among each other, they have different behaviors. They are more or less dispersed, more or less shaking, let's say, and they have a different trajectory that they follow to reach the goal. This was the case with only one group of robots, and this is the case with multiple groups of robots. As you can see, each group was defined with a different color, so that we did not consider the problem of identifying what robot is working with what other robot. Well, here you see some different combinations of the parameter. It's just for visualization purposes. I'm showing just a few examples. As you can see at the beginning, everything is very messy, but then at some point the robots start organizing their motion, and so the user is able to understand what's going on. As you can see, if in the first case the robots were converging much faster to their final configuration, and so they move in a more rigid manner, and so it's easier to understand the objective itself. Okay, let me try to go back to the presentation. It's hopefully okay. Here we go. Okay, so I can skip these videos. Okay, so here I have some results in which actually we were able to show that actually the trajectory, the shape of the overall shape of the trajectory is, as always, a very relevant effect in the ability of the user to understand what's going on. When we had only one group, so the sorry again, when based on the trajectory, the user are always able to understand correctly the goal. Regarding the timing, so how much time they need to find the correct answer, actually dispersion and stiffness appear to be very relevant, in particular when we only have one group. When we have multiple groups, the dispersion helps also in understanding correctly the destination, because it's easier to separate, to take the groups apart from each other. So here we have the p-values, actually, just put some numbers just to show you that we had numbers, but I don't feel like spending time on these numbers now. So just to conclude, to wrap up my discussion, so the question was, is it possible to communicate something through motion? Well, actually the answer is yes. So it's possible for a multi-robot system to communicate its intention through motion. What is current and future work? So if we were in a different situation, probably at this point in time, I would have had many of these questions already answered with several user studies performed in the lab. In the lab, we were ready in the middle of March, more or less, to start additional user studies, which unfortunately, as I think everybody can understand, was not possible. So hopefully I would be able to share the results soon in the future. So we would like to compare. So we were able to see that actually implicit communication can work, but we would like to compare this with explicit communication. Of course, I expect it to be worse than explicit communication, but how worse is it? And so where is the balance between implicit and explicit communication? Also, can we identify the groups? So in the last video, I showed you that the groups of robots were identified with different colors. So if we don't have colors, would the user be able to identify who is working with whom? Another thing that we are working on is different parameters to identify the characteristics of the motion. So we consider these dispersion and stiffness, which are like microscopic parameters that define each inter-robot relationship. We are trying to move towards more global parameters or macroscopic parameters, like defining a density function for the overall group. And of course, finally, we would like to perform some user studies with real robots, which was not possible so far. So hopefully we will be able to do this in the future. So with this, I'm concluding. Here are the current publications that we already have published about this topic. So you can find them online. If not, if someone wants details, I will be happy to share this presentation. And well, I thank you very much for your attention. I'll be happy to take any question.
Thank you, Lorenzo. Thank you very much for your talk and your nice presentation of, I think, your very latest results. So if there are any questions for Lorenzo.
Yeah, I have a question, if I may.
Go ahead, Dimos, go ahead.
I was wondering what type of dynamics you can deal with in this formulation of the robots, I mean.
Mm-hmm. Yeah, we didn't, yeah, what I forgot to mention.
Other issues like collision avoidance and these kind of things.
Yeah, so we started considering the concept itself, so we neglected completely, let's say, real-world dynamics and kinematics also. As you may have seen in the videos, we considered completely holonomic systems, so essentially we modeled them as double integrate, as very simple double integrators. Because, you know, at the beginning, we were not even sure that the overall concept made sense. So we wanted to understand if the idea itself could have some potential, some possibility. And then, yeah, we do need to, what we're trying to do now is to move it towards real world. So consider an environment that is not empty, for instance. And so how will the environment itself affect the legibility of the system. And yeah, non-holonomic constraints. My intuition is that non-holonomic constraints, for instance, will help in understanding what's going on, because you have a notion of direction, and so the direction of motion is interesting. So yeah, I mean, I don't have a question, I don't have an answer for this question at the moment, but hopefully we will be able to investigate these aspects in the near future.
Thank you.
Thank you. Thank you for the question.
Thank you, Lorenzo. Thank you, Dimos. I have an additional question, maybe in this line. Do you think that in the future this kind of approach could be also applied to multi-arm robotic systems and complicating the dynamic model of the robot
Yeah.
to include several degrees of freedom, parallel or kinematic chains?
Yeah, I think so. I think so. Of course, I mean, as you change the characteristics of the system, then the conclusions that you may get can be totally different. I mean that in the case of the paper I was showing with one manipulator arm with two bottles, in that case, the straight line was the less effective way to understand the motion, while in the multi-robot case that we had, actually the straight line was the most effective way of communicating the intention. So I believe that if we have multiple arms, then these concepts can be applied, probably with different numbers, with different characteristics, with different specific characteristics.
Okay, thank you very much. Any other questions to Lorenzo? Okay, thank you very much, Lorenzo, again for being part of this jam session.
Thank you. Thank you very much.
So now we can switch to the second speaker of this session, Dimos Dimarogonas by KTH Royal Institute of Technology, Stockholm, that will talk about distributed hybrid control of multi-robot systems under spatiotemporal specifications. Thank you very much, Dimos, for being here. And
thank you for the invitation. I was just wondering if you see my screen now.
Yes. Yes.
So you see my presentation?
Yes, I will see your presentation. You are not in. Okay. Okay. Perfect.
Is it better? Okay. I hope it will work now. So first of all, I would like to thank you very much for the invitation in this very interesting concept. I wish it would have been in person, but probably we can look forward to next time. So I'm going to talk about research we have been conducting in my group in the last few years, and it's about distributed hybrid control of multi-robot systems, and it is under spatiotemporal specifications. I'm going to get into most of the terminology shortly. So the background here is on control, and in particular multi-agent control. This has been a hot topic in the last 20 years or so. And the reason is that on the one hand, it has many application domains such as multi-robot systems, transportation, and smart grids. On the other, there has been a tendency to exploit computational power that has been emerging in order to go to more large-scale systems, such as multi-agent systems. So traditional control objectives in that form include consensus and formation control, which are, in my viewpoint, these are related to standard control objectives such as stabilization and tracking. So in recent years, there has been an attempt to go to more general specifications, to more general objectives, and these are called in the literature high-level objectives or tasks. And a trend in order to do this type of planning and control was to consider formal verification methods that involve formal languages, formal logic languages that impose such high-level tasks to the system. And there has been a lot of work when it comes to the single agent case. So our objective was to start going from single agent to multi-agent, and before going further to the state of the art, let's see what we mean as examples of high-level tasks for single or multi-robot systems. So for example, you can think that you have tasks of the form go to a certain point within 50 seconds, and then to another point, and then try to keep a safe distance from pedestrians, humans, and from other robots. And it might be the case that you have quantified the time deadlines and space constraints of your problem. Similarly, you can have surveillance tasks, again, which have a logical or a repetitive part, and also have a quantifiable part in both space and time. So once we started looking at the state of the art on this a few years back, we have seen that there was a lot of work on single agent and single task, single robot and single task, which involved a three-level framework, starting from the high-level formal verification language, impose a high-level task to the robot. Then, given the fact that this high-level language is involved in the discrete world, we assume that we have a discrete representation or abstraction of the agent dynamics, and then we perform planning based on model checking or graph-based tools. And then, given the discrete representation, the discrete framework on how to go from the continuous to the discrete world, implement a continuous time control sequence at the low level that fulfills the planning objective. But when we started looking at multiple agents and multiple tasks, we figured out that there were various bottlenecks to prevent us to have this in a straightforward manner. For example, one might think of distributed tasks that may or may not be coupled with each other at the agent level. We can think at couplings also at the dynamics level. We can think of limited communication and sensing also capabilities, which I don't mention here, between the robots. But what I want to emphasize is that the recent things we have been doing is also trying to have quantifiable spatial and temporal constraints. So this time deadlines and specific distances to keep or to stay away from. So the approach we have been using is that we have observed, or we have also used ourselves, that for discrete logic such as linear temporal logics, standard approaches involve model checking tools that operate in the discrete world, but they cannot treat quantifiable constraints in space and time, such as the high-level task specifications I mentioned. So our idea was to gradually go from these automata or computer science-based tools, which operate in the discrete world, to more continuous time traditional control approaches that impose, apart from stabilization, also transient control specifications to the closed loop systems. And these transient control specifications have the aim to impose the spatial and temporal constraints quantifiably, as I mentioned. We have used various transient controllers for this, such as MPC, control barrier functions, potential fields, and prescribed performance control. Today, given the time constraints, I'm going to mention only our work on prescribed performance control, but I'm going to give some highlights on some of the other ones as well. So the idea of hybrid control is how exactly to do this blending. We have high-level multi-agent tasks that have a discrete, direct discrete flavor, and we have at the low level continuous time systems. And we want to consider that we have multi-agent systems and we wish for distributed solutions. So today we have dealt in the last years with several of this type of problems, both in more classic control part and also in robotics problems. Today I'm going to talk about two approaches in robotics problems. The first one involves cooperative manipulation as the underlying system to be controlled, and time temporal specifications at the beginning. So in the beginning, I'm going only to treat time specifications for the aim of cooperative manipulation. So again, in the top here, we can see that we can have high-level tasks of a certain format that have constraints in space and time. And our approach is to consider the following formalism. We consider system dynamics, and I'm going to mention what we mean by system dynamics. We're going to aim at a discrete representation of this system dynamics in a time transition system that captures the time constraints. Then we're going to use a logic that can deal with such specifications. This is called metric interval temporal logic. We're trying to also have a discrete representation of it. And then we're going to use a type of graph search in order to derive a desired plan. And I want to mention that this is work mainly initiated by my PhD student Christos Verginis, who just defended his PhD. So the preliminaries is that we may consider that we have a time transition system as a representation of the system. Just to follow some of the tuples here, P denotes the states in the transition system. We have a transition relation between the states. In order to capture the logical part of the high-level tasks, we have the so-called atomic propositions, which are propositions of the form, for example, I'm at a certain state or not, and these have a logical Boolean aspect. And then at each state P, we wish to assign which of the atomic propositions may be true or not, and this is done with this labeling function. What is important here is that for each of the transition, we also assign a certain function that captures their time duration. In particular, in the work I'm going to show, we have an upper bound for such duration. So now, if I have this object, which is called the transition system, I can imagine that I have runs within the transition system, which are which stage of the transition I visit, P1, P2, and so on, and at which times. And if I want to go from the actual trajectory to which type of specifications can be fulfilled, I want to go from the states to the actual atomic propositions that may be true in this stage, and this is done with the correspondence to the labeling function. And I go from time runs to the so-called time words in the system. Just some more tuples before I go to the specific problem in hand. Metric interval temporal logic is a formal verification language that, apart from standard operators such as negation and conjunction and disjunction, it includes temporal operators, and these notations involve next, always, and eventually, but they need, such specifications need to be fulfilled within certain quantifiable time intervals. So that's the difference with respect to standard Boolean logics. And then I can have a path sequence. If I observe a path sequence, and now I have that these RJs belong to the set of possible true atomic propositions, we need to check if this path sequence in the transition system satisfies or not the formula that is defined recursively in the above manner. So the basic idea is more or less similar to the state of the art I showed. We have a time transition system representing the system. We have complex specification as an MITL formula, and then there are two steps. One is to translate the formula to a discrete object that captures the timed objectives, and we call this timed Bucchi automaton. And then we need to define a sort of a product that actually checks which of the runs in the product satisfy the formula, and then projects back to the time transition system to find runs that fulfill the formula. So that's the overall idea. Unfortunately, for metric interval temporal logics, we found out that there was not standard way to implement the steps 3 and 4 here. So this is another motivation from what I'm going to talk about later on today. So if I go back to my problem in hand, we consider cooperative manipulation. In this work, we have certain convenient, I would say, assumptions in order to simplify the problem, since this is a new concept with respect to such problems. We consider rigid grasp with respect to the object, and we assume that we have a team of robots rigidly grasping an object of known geometry. And this is another important point. So here I will browse quickly through some notation. We have P and eta to denote orientation, to denote position and orientation of the object center of mass denoted by O, and of the robots and effectors denoted by EI. And if I want to do some further modeling here, we have the usual kinematics relation with respect to an inertia frame. But the important thing is that I want to use the rigidity assumption in order to model the effect of the torques UI of each end effector to the center of the object of mass here. So here we have some standard dynamics equations for the object, and here we can imagine that this is the internal force that the object imposes to the system. We have this type of equation for the end effectors. Here is the torque input of each end effector, and this is the internal force inserted to the system. And a standard assumption when we have grasp rigidity is that lambda O and lambda I are related through this condition here, where G is the so-called grasp matrix. Each of the elements here is the Jacobian from the ith end effector to the object center of mass, which again through the grasp rigidity assumption is full rank. So here, based on all this assumption, I can piece and stack together the torques, the inputs coming from each end effector, and have this type of equation for the object center of mass dynamics. Here I have some noise and gravity terms as well, but the M tilde and C tilde matrices comes as equations stemming from the own mass and Coriolis terms of each of the system. So here the whole story now is I have my dynamics, I have my system, and how do I build a suitable time transition system that captures this effect? So I have the dynamics, I have rigid grasp. So the first approach is to treat the whole object as a single system, and I do this by considering what is a maximum distance element in this overall object. So this L hat denotes the maximum distance between the object center of mass and any point in the coupled system. And then the idea is to partition the 3D workspace into rectangles, and I call them PJ, and this on purpose because they relate to the states of the transition system. And the side length is indeed given by 2 times this L hat plus some tolerance I have here. So the whole story now of the transition system is to define the transition relation and define it in a way that I can quantify the time duration it takes. In order to do that, I need to define a controller that takes me between centers of the neighboring regions. That's the first idea. Another important factor for this controller is that A, I need to quantify the time it takes me between neighboring regions, and B, I need to make sure that during transportation, I remain in the union of these 2 regions. The reason being that if I allow my system to go from 2 neighboring regions through a leeway from other regions like that, I hope you see my cursor, then the formula might be violated because I might visit regions that make atomic propositions true, which violate the task in hand. So I have a transient constraint problem between regions of interest. If I want to see it geometrically here, I want to go from the between the 2 green crosses, but I want to make sure that my overall system, which is this red circle here, remains within the union of these 2 neighboring regions. And I want to do this within a pre-specified time TF, at least at its upper bound. So the whole system, the whole problem here can be translated to a guarantee that if I define a line desired trajectory that starts at the first point at T0 and wants to go to the final point at TF, I want to build a trajectory tracking controller which fulfills the transient constraints in space and time. So I have a funnel control problem essentially, and the tool we have been using is the prescribed performance control literature introduced by Behlurius and Rovithakis in 2008. And this approach essentially guarantees that apart from stabilization, I have a way to assign transient constraints to my system in space and time. And this is done by translating the error variable of the trajectory tracking problem to an error variable of the transient control problem. So here I have a way so that my E of t converges to 0 or converges to an arbitrarily small point around 0, but at the same time fulfills transient constraints in space and time. For those of you that want some that may be related to this literature, this is called funnel control in another literature coming from German researchers at around the same time. So this is the whole idea, and then recall that we want to build a controller that takes me between two neighboring regions, between the center of one region to the center of the other, under these dynamics, and respecting the fact that I need to stay within the union of these two regions, do not cross another region, and I want to do it in a pre-specified time. So the whole idea is to define the error as the difference between the center of the object of mass, for which I have the dynamics, and the desired trajectory. And this is a time varying error in the sense that my desired trajectory ends at the desired point at TF. So I have this objective, and with certain tools that we use again from the literature, we can design actually a controller which is decentralized for its end effectors part and achieves that. I'm not going to get into the details of this, but instead I'm going to recap now how we use these controllers. We use them in order to define for this transition system the transition relation function. This gives us ways to go between neighboring regions of P, and we know gamma, we know the time it takes to go between neighboring regions. And then we use standard tools in order to translate this part to a time bookie automaton. Unfortunately, I'm not going to get into the details, but there are no standard tools to go from T and phi, which has the automata representation AF, to a product, but we have also implemented this. And then in the product, we need to find runs which are accepting in the sense that they fulfill the formula. Then the product, what the product gives is accepting runs that fulfill the formula, but at the same time are runs that can be projected back to the transition system. So here I can find if there exist accepting runs that fulfill the formula into the transition systems. These are translated with sequences of regions and times I need to visit them. So then I go back to my the sequence of continuous controllers that implement that. So in order to see what type of specifications we can deal with, we have here, imagine that we have now 16 regions. We have divided the workspace in 16 regions. We have a system that starts at P1 with two manipulators rigidly grasping an object. We have partitioned the workspace into 16 regions, as I said. And here we have blue and green regions. These are regions of interest. And we have obstacle regions in 6 and 10. This is with this pink or light red color here. So my MITL formula can be like that, for example. I want to always avoid obstacle regions. That's the first part. And I want to eventually visit the green region within 50 seconds. And once I do that, after maximum 20 seconds, I want to visit the blue region. So this is the type of specifications we can achieve here. Unfortunately, I still, after so many years using Beamer, I still cannot have videos, but I will try to do this indirectly with PowerPoint from current slide, maybe presenting. Do you see this now? The video? Oh, no.
No, we cannot.
Okay. I will stop this. Let me check now. So I'm here. I didn't stop sharing, so this is sorry.
Don't worry, don't worry.
I will share again. Now?
Yes.
Okay. So perhaps this is the logistics are not optimal here, but on the right on the left, there is an instantiation in our lab for a smaller version of this experiment. On the right, there is, I cannot play the two videos together, unfortunately. There is a virtual simulator we have developed in how to implement these systems. So this is just to showcase that we have done real experiments with this. We have a smaller version of experiments with ground robots. We have the more ambitious version of the experiments that I described in the slides for aerial robots as well through one of the projects we had. I'm going to try to share the original now. Stop sharing, share, and perhaps I will not move back to videos. So view full screen. I think now you see the presentation, right? So what we have achieved up to now is to have time constraints, quantifiable time constraints, but the spatial constraints aspect was kind of indirect. So we started thinking, okay, why don't we try to use these funnel-based controllers, these transient controllers in space and time, also for spatial tasks that impose quantifiable constraints in space. And then we became aware of another type of logic. This is called signal temporal logic. And indeed, this is a logic that imposes constraints both in space and time. And we have been working on this for multi-agent systems under various types, both global tasks and also locally defined tasks for couplings or not in the last years. I'm going to briefly present today item 4 here, which is how to use this PPC type of approach in order to have local signal temporal logic tasks for multi-agent systems. But I want to mention that there is a more popular, I would say, approach in controls now for transient objective, which is the control barrier function approach. We have been using this as well recently, but I'm not going to refer to this today. So we have the motivation here, and I should mention that this is mainly work initiated by my student, by my PhD student, Lars Linderman. He's going to defend his thesis in October. Here we have tasks which might be collaborative. We still consider multi-agent systems, but I want to mention, to emphasize that we have constraints in both time, as I mentioned earlier, and space. And how to implement this is that the computer science terminology goes from atomic propositions to so-called predicates. These are still Boolean variables, and they are associated with functions of the state. These predicates are true or false given the sign, the positivity or negativity correspondingly of this function. So if we have a predicate, and you can imagine a predicate is what we wish the system to do, for example. If we have a predicate that our state should remain within a ball of radius epsilon, then the obvious way is to define the corresponding predicate function as the difference between epsilon and the norm of x. So if x fulfills the predicate, then h is positive, so mu is true. And of course, this is a simplified way to do this. We can use these notions recursively now. First, the notion of predicates in order to define a certain syntax for signal temporal logic recursively. We again have negations, disjunctions, until, eventually, and always operators, and we can define many more operators through this. The semantics are given essentially in the same format as LTL and MITL, but what I want to emphasize here is that this type of approach gives us a sense of robustness. So apart from the fact that a certain function tells us if the predicate or the formula which is defined recursively based on the predicates is true or not, we have a way to say how much the system fulfills a formula, and this is given by a certain function which is called the robust semantics. It is related to a formula phi and a trajectory x, and there are ways to define this function rho in a way that its positivity, its strength, is associated to how strongly, how robustly the system implements the formula. And you might already imagine that its negativity gives us a hint of how much we violate it. So an example here that I just to to give some hints on what this rho phi might mean. We have here the same signal and 3 examples of it. And here we have phi1, phi2, and phi3, 3 formulas. The first formula is that eventually between 3 and 5, the system fulfills that it is between 2 and 3. We can see that at some point the system is indeed between 2 and 3. So it fulfills the formula, and there are ways to define what is the robustness of this fulfillment. So here it can be calculated to be 0.5. I'm not going to get into the details, but what I want to get is that the second formula tells us that between 2 and 6, I need to be between 0.5 and 6 always. This is what this G function means. So here I can see that at many points in the trajectory, I'm very close to not fulfilling the formula. I always fulfill it, but I have a very low robustness. And this is captured by this 0.01 case. And then in the third case, we have a case that the system does not fulfill a formula. Here we just shrink where we always need to be between 1 and 2. We have obvious cases that the system is not within it between 2 and 6. Here we can, based on some of the definitions we have in the literature, we can define the robustness as -1. So the system does not fulfill the formula, it violates it with a negative robustness -1. Just to give a hint, this is given by the maximum deviation here, which is at 3. So there are many ways in the literature to define this robustness. This is an ongoing research, what are the most meaningful, but today I'm going to give some hints on what we have been doing for multi-agent systems. Long story short, and related to the defense of Anna yesterday, here we do consider dependencies between the tasks of the agents, and we consider the case that we may have conflicts between between such dependencies. So we consider local tasks, local signal temporal logic tasks, but at the same time there are dependencies between the agents, both at the task and the dynamics level. So in order to give a little equations here, we consider M agents. We have dynamics of this form, Xi is the state of agent I, but we have couplings which are related to elements of this type. These are couplings which might be induced in the system. So for example, in collaborative transportation, I might have such dynamics between the arms or the mobile robots in hand. But there might be couplings that I induce in the system to have certain properties, certain low-level cooperative control properties, such as collision avoidance. And here we consider a certain fragment of STL. We didn't consider at that point the whole fragment. In particular, the timing constraints should have a certain type of synchronization. Here we have moved further than that in recent work. And we consider a bottom-up approach. So each agent has its own task phi, but now we have, apart from the dynamic couplings in FIC I mentioned previously, we have also couplings in the tasks. So here, agent phi may depend on other agents j, and this x phi takes I and all other agents that its corresponding formula depends on. So a first approach we have for this is to consider how to cluster, how to decompose the team of agents into clusters that are related to the formulas that are dependent between them. So a simple example here is that if I see phi1, phi2, phi3, and phi4, 1, 4, and 2 are dependent on each other, 3 is independent, so I can divide the system into 2 clusters. We have done it here in an undirected fashion for those that study multi-agent systems. There are ways to consider also directed graph clustering in this type of problems. So there are various approaches we had in the solution. The first approach we had is to consider that we have the simplified assumption that for each of the clusters, agents are subject to the same formula. So we have here a partial centralized solution. The benefit is that we can define closed loop controllers such that not only each of the agents satisfies the formula, but it can do so with a certain degree of robustness Ri that is actually predefined. So if we have the convenient assumption of a partially centralized system, we can actually design the controllers such that we have satisfaction of the formula with a certain degree of robustness, which is defined a priori. Now, the more interesting thing, of course, comes when we have conflicts, and this is when we might have the case that we have different formulas, in the same cluster, and here we define a hybrid controller in order to resolve such conflicts. The bottom line is that we cannot guarantee positive satisfaction, but what we can guarantee is that under our approach, the violation, that the potential violation is minimized. So I'm not going to get again into the details. As I said, we use these prescribed performance controllers. Here we associate these potential funnels of the controllers with sub-formulas consisting that are a subset of the whole formula, and we have instantiations of these controllers when the corresponding sub-formula is to be fulfilled. This is for the first case, and as I said, for the first case, we can actually guarantee, first case being we have the same formula for each cluster. So here we can actually guarantee that we can design this controller UI in a way that all formulas are satisfied within the cluster, and it is done within a certain degree of robustness, not that this Ri does not have to be the same for each agent in this case. The more interesting case comes again when we have different formulas that might be possible dependent and conflicting, dependent because they are in the same cluster and potentially conflicting. Here, if we start using the same approach as previously, we might end up in situations that the closed loop system will stop fulfilling the funnel. That means that this leads to a violation of the formulas, and there are two options we have here. The first option is to relax the funnel, to make the funnel bigger, and this is what we do initially. Of course, given actuation constraints, we cannot keep on doing this for the whole time. So there is a certain deadline for that. If this is broken, we keep essentially, broadly speaking, we keep the funnel at its maximum parameter deviation, but then we allow violation. So we allow our Ri to be negative, and the main result is as follows: that given this strategy, which is repair the funnel, if we reach its maximum capacity, then we allow for least violating solutions, we have the following result. We can again have a say of how much we satisfy the formula if the resulting Ri is positive, or how much we violate it if it is negative, and we have the following results. So the first case involves the case A I just mentioned, but then for the second case, we can actually guarantee that the robustness is lower bounded and maximized under the strategy we have used. So here is another example that we also have the videos of this, an actual experiment we had in our lab, and the videos are indeed online. We have a collision avoidance parameter here, which represents the low-level dynamic couplings between the agents. We have noise in the system to indicate the robustness, and we have a perfectly holonomic system to mitigate for the complexity of the problem here. And I just want to mention here what we mean by potential complexity of the tasks. We have 3 robots, R1, R2, R3. So the tasks in hand are defined as follows. In the top, I specify the tasks verbally. In the bottom, you can see what this means in the semantics of STL. So in the first part, R1 wants to go to A2, R2 wants to stay close to R1 and R3. There is a typo there, sorry for R2. And R3 wants to go to A1. So R1 and R3 want to follow their objectives to go to a certain point. R2 wants to move that by seeing R1 and R3, it wants to stay close to them. So here you can imagine that if this epsilon, which is how close R2 should be to R1 and R3, and how close R1 and R3 should go to their individual final states, if this is small, I may have a formula violation. So here, this is the first part where this robustness approach is important, because I want to mention that previous approach to formal methods-based planning would halt in this occasion. They wouldn't move further in this. So we have a way to keep the system moving without resetting, without manual resetting, and with a guarantee of a minimum violation. Of course, it is debatable what is the best robustness metric here. The second part is to regather all of them in the center. And then the third part, and we have also timing constraints for everything here. And the third part is that R1 wants to go to A3 and stay close to R2. So R1 has an element that wishes that it stays close to R2. R2 wants to go to A4, and R3 wants to go back to A5. So if I had the chance to show the video, I would show that they actually regather, R3 goes back to A5. But here there is a conflict, and there is a conflict between how close R2 stays to R1 and how R2 goes to A4, and at the same time indirectly takes into account the energy, the input R1 induces to it in order to have this behavior. So the thing here is that if we initially give less importance to the robustness of R2, of the specification of R2, we give a lower robustness that we want for R2. It actually obeys essentially what R1 wants to do, because R1 here in this experiment has a much higher initial robustness. So this is an interesting artifact that it gives a sense of Pareto optimality on how we define initially these two robustness metrics. So I will try to show the video after this in the end, just to finish, just to conclude the talk. I just want to mention that we have moved from prescribed performance to control barrier functions, in particular to time varying control barrier functions. What I silently didn't mention is that we cannot deal with until operators in the previous case, but we could with control barrier functions, and this is recent work we have presented in 2019 and this year. And actually, we can retain the properties of robustness and computational efficiency that I briefly mentioned. I just want to mention that I didn't have time to mention that this has been also part of an EU project I have been coordinating. It ended up 2 days ago, 30th of June. Actually, here there is a lot of integration of this type of control and planners with real-time navigation of robots and also with robot-based vision. In my lab, we have done it with a mock-up. In this project, to which I invite the interested viewers to see the results of, we have done it with actual real-time perception. So as a general observation, I presented how to use transient-based continuous controllers for multi-agent planning and control under high-level spatiotemporal logic specifications. Many other approaches, many other cases of the same thing can be found on my website. And with that, I wish to thank you for your, I didn't count the time. I'm always much later than I should, so I think this was the case. But I thank the organizers for being generous. Not I will try while trying to get questions. I will also try to show the video of the last experiment. So let's see. Probably you can see it, or?
Yes.
So this is this is some this is the experiment essentially I described. We have some these extra robots act as moving obstacles in order to showcase also the collision avoidance aspect, which is both between the 3 robots and also between moving obstacles in the environment. So here you can see the last part that the robot 3 goes back to A5. Here you can see the part that the middle robot with the lower robustness requirement goes actually sacrifices more its objective in order to go close to robot 1, which has a higher robustness, a higher initial robustness requirement. This is just to also mention that we have done experiments on this theme with aerial manipulation, but I'm not going to get to that in this talk. So yeah, I stopped sharing now. So thanks.
Okay, so thank you very much, Dimos, for your talk. Very, very interesting. And any questions? So there is something coming from YouTube. First question. How difficult is to remove the assumption of accurate tracking? What happens if not, if they are not fulfilled? For example, the robot model is not accurate, or there is a human in the environment making the robot stopping?
So I assume that they refer to the cooperative manipulation part, because this is where I talked about tracking. So this controller have a certain degree of quantifiable robustness, and I would assume that we could use this there. Of course, in the problem of tracking is also how large you allow the derivative of the desired velocity to be. And this is something I didn't have time to talk about. So this is important in how much robustness we can tolerate in this system. Additionally, we have, in implementation, we have dealt with collision avoidance at the low level to avoid humans and other moving obstacles, but this has not been part of the publications, let's say, because first of all, we couldn't have guarantees, and secondly, we didn't think that the experimental part would add more to the overall framework here. So it wasn't so meaning that it wasn't as in Lorenzo's talk that the human actually gives inputs to the system. So the human was more like
another passive agent,
bypasser, let's say, someone being in the area. But I just want to mention that for the overall approach, the reason we went to transient controllers is exactly this one, that they have by definition a certain degree of robustness at the expense of higher actuation capabilities requirements. So there is a trade-off there that I also didn't talk about. But there is some robustness that we can claim and actually guarantee.
Guaranteed. Okay, so thank you. Next, do you think the last control law to be suitable for real robots and with online spatial and temporal constraint post? It has alphabet deadlines changing online. Yeah,
that's. This is something we have also dealt with. Theoretically, yes. Practically, there might be problems in how fast you change the requirements, of course. So if the requirements, if the updates in the specifications are not fast enough, not only for the computation, but for the real-time change of actuation there. So there needs to be some smoothness in how we change the actuation practically. So if you impose specifications to the system very fast, then this will not work in practice with these controllers, at least. But we have seen that with reasonable rates. So there is another project that we actually have human inputs to the system remotely, like not in the virtual reality like Lorenzo showed, but remotely through a type of app, let's say, not a product, but there is like a computer software that does it. We have seen that if the humans change the specifications at a reasonable rate, let's say, at a rate that you would expect, that they don't want to play with the system, but they really want to change the specification for some reason, then this worked quite efficiently. If someone changes the specification really fast, no. But I don't have a quantifiable answer to that.
Okay. Yeah, in third question is very general, asking about drawbacks, limitations of this last approach.
Limitations, what was the first word before limitations?
Drawbacks.
Drawbacks.
So it's like, I mean, if there are, you know, counterparts or more in general future works,
yeah,
we are going to do to improve them.
So if I see it from a, let's say, class control perspective, it is related to how much guarantees you can give from a control theoretic perspective, because there, what I didn't mention is that we make some strong controllability assumptions about FNG in the system.
Okay.
This is more and more relaxed the more research we do, and the more research other people are doing in this type of problems. From the robotics, from the application, let's say, perspective, I would say that the main drawback is what we have seen also in the project I mentioned, is on the integration with other modules, with perception, real-time perception modules and software architecture modules. So it's not, if with automata-based representations, it was more straightforward to implement this. At the expense of what I didn't mention, with automata-based approaches, you have this exponentiality in scalability that you cannot get rid of. You get rid of this here, but at the same time, because you operate completely in the continuous time space, it's not straightforwardly integratable. This is the, at least from my experience now, this is the main, from a robotics application viewpoint, this is the main aspect that we need to work more on.
Okay. Thank you very much. Thank you very much for the talk and also for the very interesting and deep discussion. We thank also the guys from YouTube that are very actively asking questions to all of you.
I didn't see this. I wasn't aware that they can pose questions on YouTube. So
yeah, they have the chat, so they are asking really, and someone of us is just reporting to you. It has been done.
They can also contact me for the presentation or any other information they want.
Sure, sure. Someone of us will ask you the presentation after.
Okay.
Thank you very much, Dimos, again for being part of this event. And now we are moving to the next speaker, Paolo Salaris from University of Pisa. So I'm very happy to leave the stage to Paolo, a colleague of mine. And okay, Paolo, we are already seeing your screen. So
yes, okay. I am trying to share my presentation. So now you should see my presentation.
Yes.
Isn't it? Yes. Okay. So morning, everybody. My presentation today is about a solution I proposed to the active sensing control problem for robotic systems. This work has been done in collaboration with some colleagues in Rennes, in France. There are Paolo Buffo Giordano, Marco Cognetti, Marco Agravi, and Claudio Paccherotti. It started when I was a permanent researcher at INRIA in Sophia Antipolis, near Nice in France. Now I'm still working on the subject here in Pisa. So as we are talking about active sensing control, I would like to start with some definition coming from the literature. So active sensing was defined the first time by Bajixi in 1988 as the problem of intelligent control applied to the data acquisition process. For that, one needs to define and measure parameters and errors from the scene, which in turn can be fed back to control the data acquisition process. This is a difficult problem because many of the feedback parameters are context and scene dependent. Think about camera parameters, illumination, scene reflectance, and so on and so forth. And is important because this definition tells us that one does not spend time on processing and artificially improving perfect data, but rather on accepting imperfect noisy data as a fact and incorporating it into the overall processing strategy. 30 years later, based on all the results of the last 30 years on research in this topic, the same author and other colleagues gave a new definition, this time more oriented to the behavior that characterizes the active perceiver than on the underlying data acquisition process. So an agent is an active perceiver if it knows why it wishes to sense, and then chooses what to perceive and determine how, when, and where to achieve that perception. So virtual and in practice, any intelligent agent that has been developed today satisfies at least one of these components. And hence, without any other constraints, this definition will not be useful to identify what is an active perceiver. The key component, is indeed the Y component. An actively perceiving agent is one which dynamically determines the why of its behavior and then control at least one, but not necessarily all, of the what, how, where, and when for each behavior. The Y component basically requires the agent to reason about the so-called expectation action tuples, to select the next best action, for instance, in terms of estimation improvement. Okay. In the 18th, robotics was defined as the science which studies the intelligent connection between perception and action. This is very clear from a classical control scheme. For instance, in this case, there is a model that is identified by some state variable, parameter, and disturbance. There is a sensor reading from the onboard sensor, for instance. There are control inputs. These two signals are used in an observer in order to identify parameter or disturbances, or also to estimate the state that usually are not given directly by the sensor. And then these variables are used to define suitable control actions that are able to accomplish for accomplishing a task. There is an evident action perception coupling here. Indeed, especially for nonlinear system, actions influence estimation performance. This is very clear also for observability theory, that in turn influence the correct definition of actions. So this action perception coupling that exists in this very simple control scheme needs to reason about the expectation action coupling in order to determine what is the best next action in order to improve the estimation accuracy and the precision, and hence to better define the control action that at the same time influence the perception and the estimation process. This seems to hold also for humans. There are several papers that mention this correlation between the noise that affect our sensors and actuation and the action that our brain design for accomplish a task. In particular, this is evident from this paper, where authors showed that by incorporating state-dependent sensory feedback, the optimal solution incorporates active sensing and is no longer a pure feedback process, but includes a significant feed-forward component. Our brain, indeed, seems to dedicate a lot of effort for reducing the negative effects of noise in both sensing and actuation during the execution of the task. And the feed-forward component is in part generated to achieve this goal, and not only, as Professor Verschuur yesterday explained us, there is also a prediction in this feed-forward component. But part of this component, I think, is also for reducing this negative effect of noise. Now, in order to solve any active sensing control problem for a robotic system, we need to define a metric, okay, to measure the collected information along the path. Okay. In my work, these metrics come from the observability analysis. So in general, most of you maybe already know. So a nonlinear system is observable if from the future and the future outputs and inputs, it is possible to observe the initial state. This is true if the observability grammar, which is a matrix I show here, okay, is full rank. And a function of the eigenvalues of this matrix can be used as a metric, so as a measure of the information collected along the path. However, in practice, we are much more interested in reconstructing the current or future state instead of observing the initial one. And hence, we need a measure for quantify the information collected about the current or future state. This can be obtained very easily by pre and post multiplication, by pre and post multiplying the observability Gramian by a matrix, which is called also sensibility matrix, to obtain the so-called constructibility Gramian. The main difference between these two Gramian is indeed in this metric, which is the sensibility matrix. Here is defined in terms of the current integration time and the final integration time, while in the observability Gramian, this metric is defined in terms of the current integration time and the initial extreme of integration. The sensibility matrix basically express the sensibility of the state trajectory solution with respect to small variation of the initial condition or of the final one, depending if you consider the sensibility metric for the observability Gramian or for the constructibility Gramian. Now, if we consider as an observer the standard Carlo filter, is it possible to show that the constructibility Gramian is also the solution of the Riccati differential equation, and hence is not only a measure of the information collected along the path, but is also a measure of the uncertainty about the state estimation. Okay? So if we consider the Riccati matrix Riccati differential equation, which is this one expressed in terms of the inverse of the covariance matrix, and we consider the process noise negligible or very small or zero, we can obtain an explicit solution of this equation in terms of the inverse of the covariance matrix, and this solution is provided here in this slide. So basically, it's the sum of two terms. The second one is exactly the constructibility Gramian from T0 to T, which is the current estimation time. And it's possible to recognize that this is the constructibility Gramian because here there is the second extreme of integration. The first term is basically the a priori information or the estimation uncertainty about the initial state estimate, but pre and post multiplied by the sensibility matrix, and this matrix play a role of translating this information on uncertainty at the current time t. So basically, this P0 minus 1 can be seen as the constructibility Gramian from minus infinity to T0. And so basically, all these solution of the Riccati equation can be seen as the constructibility Gramian for minus infinity to the current estimation time. So there is a relationship given by the constructibility Gramian between the collected information on the path and the estimation uncertainty. So based on this metrics and the strict relationship with the extended gamma filter, but also with any other observer, for the standard gamma filter is a strict relationship, but for sure the constructibility grammar has a general validity, so is good also for other observer. I define an optimal sensing control problem, where the objective is to maximize the smallest eigenvalue of the constructibility grammar, okay? So determine the control action that maximize this function. But in order to make the maximum, the maximization problem well defined, we also need to include another constraints. Here I consider the constraints that the energy that the robot can spend in order to improve the estimation accuracy and precision is limited to a given value E bar. Okay, why I need to introduce this constraint? Because the smallest eigenvalue of the constructibility grammar can grow and go to infinity with the time. So we can spend a lot of time okay, to increase this value, and there is no a maximum. Okay, of course, other constraints can be used, for instance, the length, or we can also consider other kind of constraints, like, for instance, to limit the control U, and to limit also the time that the robot has in order to accomplish the optimal sensing control problem. The problem with the smallest eigenvalue, which is, I think, the best function of the eigenvalue of the constructibility grammar in order to define the measure of uncertainty as a problem, especially when two eigenvalues coalesce, in the sense coincide. So it is not differentiable, and hence, if we would like to solve this optimization problem by using classical gradient-based method, of course, the fact that in this situation is not differential may create some trouble. So in order to avoid this problem, we consider the Schatten norm, which is a differential approximation of the smallest eigenvalue of the constructibility grammar, which is defined like that, where the exponent here is negative as much as possible, but of course we need to choose with some limitation. And if the other eigenvalue are very far from the smallest one, basically this is a good approximation of the smallest eigenvalue, but is differentiable all the time. Then the cost, of course, depends on the state of the robot, which is unknown because it is the objective of the estimation process that underlie any control scheme. And there is an observer that improves online the state estimation of the robot. So the only possible solution in this case is an online solution, which is the only reasonable option. So we need, of course, to cope also with the real-time implementation of an optimization problem. And basically, the optimization of the future trajectory of the robot should be done starting from the current estimate provided by the extended Kalman filter. So we need always to keep into account this new estimation provided by the Kalman filter, and based on that, plan the next future optimal path. To avoid the integration of the sensibility metrics backward in time, because maybe I didn't mention that, but the sensibility metrics that is here is not always explicitly known, but it's possible to determine it by integrating a matrix differential equation. Unfortunately, for the constructibility Gramian, this differential equation must be integrated backward in time. So in order to avoid this problem, we can decompose the constructibility Gramian in order to express it in terms of the observability Gramian that has a sensibility matrix, but this time for the observability Gramian, this matrix can be integrated forward in time. To do that, we need to use the semi-group property of the sensibility matrix by substituting in the integral and collecting the sensibility matrix itself. We can see that now here this integral is the observability gradient, because here there is the first stream of integration, and here there was the second stream of integration. And so I can write the constructibility gradient now in terms of the observability one. And this expression has also a very insightful interpretation. Indeed, the first term is the a priori and past acquired information. It can be freely obtained by the extended Kalman filter. Of course, it is a constant at time t, because this depends on the past followed path by the robot, and cannot be optimized anymore. And is, of course, the information about what? About the current state at time t, where the robot is at the current time. This second term, which is expressed in terms of the observability gradient, is the information yet to be collected along the future path about the initial state. And the initial state for the observability gradient is not t0, but is t, the current time. So these two terms basically express all the information I collected in the past and I will collect in the future about the current state. And then by pre and post multiplying by sensibility metrics, I can translate all this information at the end where I would like to minimize the maximum estimation uncertainty expressed by the smallest eigenvalue of the constructibility gradient. Of course, also these metrics depend on the state of the robot and hence on the planned trajectory. So the way of translating this information at the end depend on the trajectory, even without any measure in the future. So even if G0, so the observability gradient in the future path is 0. Okay, so in order to reduce the computational complexity of the optimization problem and hence better cope with an online implementation of the problem, we restrict our attention to the case of nonlinear differentially flat system. Now, the most of the interesting robotic system have this property, so the solution I propose is still sufficiently general. A system is flat, is called flat, if it is possible to determine a set of outputs called flat outputs, such that all the state and the inputs of the system, of the robotic system, can be expressed as a function of the flat outputs and a finite number of their time derivatives. So basically, is the same as to have an explicit solution of the differential equation that expresses the model of the robot, and hence I can avoid to integrate it along the future path in order to calculate the observability gradient. Then I parameterize the flat outputs and hence all the input state of the robot in terms of B-spline. B-spline are linear combination through a finite number of control points of polynomial basis. We also assume that the control point of the B-spline move accordingly to this very simple differential. So the objective and the solution I propose is an online gradient descent algorithm with a concurrent estimation scheme, an extended Kalman filter in our case, in order to minimize the maximum estimation uncertainty. So basically, what I propose is a hierarchical stack of tasks, because I want to maximize the information collected on the path, but at the same time, I would like to respect the constraint on the limited energy that the robot has in order to accomplish this task. And as soon as I have a new estimation of the state of the robot provided by the observer, I need to provide another future optimal path that maximize the information and hence minimize the maximum estimation uncertainty. Of course, these two choice of B-spline and flatness comes with some drawbacks. and we need to introduce two more tasks in the stack of tasks of the hierarchical stack that I would like to provide. The first one, I call the first one coherency. Okay, so basically the future optimal path must be calculated starting from the current estimation provided by the standard Kalman filter. However, the standard Kalman filter that has been solved problem are not talking each other. Okay, so we need to include another task, another constraints that impose that the current, the initial point of the future path, which is here, okay, coincide with the current estimation provided by the extended Kalman filter. In this way, we can plan the optimal path from the right state estimation. The second one is called flatness regularity. So we need to guarantee that the flatness regularity is achieved, because the flatness is very interesting, because we can have a solution of the nonlinear system without integrating the dynamics, but there are some intrinsic singularities. For example, for a unicycle, these singularities coincide with the forward velocity of the unicycle equal to 0. So we need to guarantee that the unicycle does not stop. So its the forward velocity must be always no 0. And in terms of B-spline, this is equivalent to have a caps in the B-spline. So basically, if we would like to guarantee the flatness regularity, we need to avoid this particular characteristic in the path. And for B-spline, for instance, this is characterized very, very well. For instance, if you consider this control point, in order to avoid caps on the spline, you need to avoid that the control point go on the red line. So, for instance, in this case, the red control point go on the red curve that can be characterized analytically, and there is a caps here. The same if move here, or if it's move in the intersection between these two curves. In this case, we have two caps. To avoid this, we can introduce a sort of potential function that basically avoid for the control point to move on the corresponding curve, red curve, basically. So at the end, we have 4 tasks, okay? And I decide a hierarchy about these 4 tasks. The first one is coherency. We need to guarantee this the first, because we need to provide an optimal solution from the current real state estimation provided by the observer. Then I need to guarantee also the regularity, because it's based on the regularity that I can basically calculate the constructibility gradient and all the other tasks that I need for finding an optimization, an optimal future path. Then I need to respect the fact that the energy is limited. And then the last one is the maximization of the Schatten norm of the constructibility gradient. This is the overall control scheme. So basically you have the robot. This is the real robot, okay, for which we have a model. So we have an onboard sensor that provides some measurements. These measurements, with also the control inputs, are given to an extended Kalman filter alongside the initial covariance matrix. The extended Kalman filter provides an estimation of the covariance matrix. This can be used inside the CG maximization as the a priori information collected along the past path. So basically, it's a sort of memory about the collected information, and also the estimation of the state of the robot. This state can also include some parameter, for instance, for set calibration or for scene reconstruction. Here there is the optimization problem expressed as a stack of tasks that give rise basically to the control load that move the control point and shape basically the B-spline in order to determine the one that maximize the information, the collected information, and respect all the other higher in terms of hierarchy constraints. These control points are used based on the flatness in order to determine the control load that are given to the robot. These results are published in this paper. I would like to show some simulation. In this case is the case of self-calibration, is a problem of self-calibration. So there is a unicycle vehicle that measures two square distance with respect to these 2 points on a plane, okay, and has to move in order to maximize the collected information. About what? So on the left, this path, which is the initial one, is provided in order to maximize the information about only the state of the robot, so x, y, and theta. Why this one is the optimal path in order to maximize the information about the extended state. So there is x, y, theta, but also the calibration parameter that in this case are the radius of the wheels and the interacts between the wheels. So this is the simulation. You can see also how basically the optimization is also improving the future path during the execution, just because the extended camera filter is provided a new estimation, which is better than the one I get before. So you can see also here how the precision, the estimation error is much improved along the this path with respect to this one, just because here I consider in the state also the estimation parameter. Here we have a measure basically of the maximum estimation uncertainty. So basically, if this value is big, means that the maximum estimation uncertainty is very small. So here we have an improvement also in this case. And then we also apply this method to a quadrotor moving on a plane. And in this case is measuring again two square distance between 2 points and needs to estimate its configuration. In this case, we also add another constraint. Indeed, the noise that affects the sensor smoothly increases, going to infinity beyond a given distance. So basically, just to say that our sensor has a range. And we can see how this method automatically respects these constraints of remaining inside this range, because if the robot go outside, basically the information go to 0, and you cannot improve the estimation accuracy. You can see also here, here there is the optimal path, and here is the initial guess that I use to determine this optimal path. Okay, so this is basically a not optimal path in terms of estimation uncertainty. Okay, so we have also extended this methodology to the problem of share control. That I will give you a sketch of how this method that I show you can basically tend to this problem, but maybe because of time I cannot show everything. So basically, if you consider the stack of tasks that I showed before, just for maximizing the information collected along the path for the robot, what we add is just another task just before the maximization of the constructibility gradient, which is the user's inputs. The control scheme change like that, Okay, so basically what we add is the user input here in the stack of tasks. And then there is, of course, the human operator that can interact with the robot by acting directly on the control point of the spline that the robot is following. And of course, the human operator is also receive a feedback about the current quality of the future information that the robot can acquire by following the planned path. So the goal is to combine the skills of a human operator in accomplishing complex tasks with the capability of a mobile robot in autonomously maximizing the information acquired by the onboard sensor for improving the estimation. So in this case, the human operator modifies at runtime property of the cyclic path. So in this case, we consider a cyclic path instead of an open B-spline. This then comes with some problem, but because the operator that try our methodology basically say that using this closed B-spline is not very useful, but we learned this after all experiments, so we can improve it. For instance, a property of the B-spline can be the barycenter of a point on the B-spline. The path is concurrently adjusted to maximize the acquired information, and the user is also provided with guidance feedback about the quality of the acquired information. In this case, we consider two kinds of feedback. One is the visual arrow on the screen, and the other is a force that in the direction of the maximization of the acquired information. We have considered two scenarios. The first one is power grid activation. So the user has to activate 4 switches represented by tiles in this scenario in a certain order. The next switch to activate is red. When activated, it turns green. A switch activates when the real robot passes over it. So very small to the center of the tiles. But the problem is that user only see the estimated robot position on the screen, is not able to see where is the real robot with respect to the switch. Basically. The second scenario is the infrastructure monitoring. So the user in this case have to make the real robot visit 100 tiles on a factory floor. But also in this case, the human operator can only see the action of the estimated robot. So at the end of the task, maybe the real robot, the estimated robot accomplished the whole task. But if we see what the real one is doing, maybe some tiles remain outside, so is not visited by the real robot because the estimation uncertainty is not very good. Okay, so I can just switch to the final results. So before that, we consider also 4 experiment modalities. So the first one, in the first one, the maximization of the constructibility gradient task is removed from the stack of tasks. And the user receives no feedback on how improving estimation. Okay, so it's really in open loop and is just looking the estimated robot position on the screen. In the second case, we include also the maximization of the constructibility gradient, but the user receives no feedback on how to improve the estimation. So in this case, there is something that tries to increase the information, but the user is not aware about that, and so is again in open loop. And in the third and fourth cases, we consider also feedback. In the first case, an arrow in the screen pointing in the direction of the maximization of the information. The second one is a force feedback provided by the omega-6 haptic interface. Okay, so these are some results that we obtained. So I would like just to show some also drawbacks and problem that we need to solve to make this machinery working in a real scenario. So, for instance, in scenario 1, so there is the switching that the user needs to activate in the end condition, so where there is no maximization of the information collected on the path, and there is no feedback to the operator. Basically, the estimate of the real robot is very poor. So there is several passes in order to switch, and the user become quickly frustrated. So in some sense, the feedback and the maximization of information is useful for this case. For scenario 2, there is no feedback at runtime about the tiles actually visited by the real robot. And this implies less importance of the info feedback in the sense that in this case, so the user is always is able to see the estimated robot on the screen. It seems that the estimated robot on the screen accomplished the task, but maybe the real robot is not. And of course, the operator receives a feedback about the maximization of the information, so the quality of the estimation. So if the force or the error is very big, it means that the collected information is not a lot, so the estimation is maybe very poor, and so the real robot cannot accomplish the task. But for instance, a couple of users out of 10 judge the feedback, visual and haptic feedback, useless and distracting. Maybe they do not understand very well the meaning of the feedback, or maybe it's our fault, because indeed for a user that is not aware about observability, I think, and is for sure, it's very difficult to understand what is the objective of this feedback. So maybe another problem is to make the user understand the potentiality of following the feedback. Okay, and another problem is that it's difficult to accomplish the task by only moving the closed B-spline by acting on the centroid. Maybe a possible solution is to consider B-spline which are open B-spline, and to give the possibility to the user to control the final point of this B-spline. Also, this paper has been accepted to the RAL very recently, so you can find other explanation here. So I would like just to conclude with a few remarks. So, of course, we need to include an algorithm of obstacle avoidance in order to be sure that, in order to apply this method to real cases. But in my opinion, a complete robotic system must include a sort of active perception, but we need to answer to this question. So how coupling with the task that the robot must follow, maybe we can do in some sense as humans. So we have a feedback, which is for the task, and a feed forward can try to improve the estimation uncertainty. Then we need to consider what are the algorithm and numerical method that enable an online implementation of active perception, because this active perception must be done online. So we need to cope with the real-time constraints. In this work, I didn't consider the negative effect of process noise. So basically, I include the process noise, but the process noise acts equally on the whole state. So basically, the optimal path that I consider here is also optimal in case of this kind of process noise. But what if you have an actuation noise? In this case, basically, for nonlinear system, this noise acts in particular direction, so maybe we can do something in order to avoid these negative effects. And thence, I would like to also extend to multi-robot system, but in this case, we need to decentralize this optimization method. So I finished my presentation. So thank you very, very much for your attention, and I'm here for answering some questions.
Thank you, Paolo, for your interesting talk. Any question to Paolo?
We can also go for lunch, as you want.
Yes, everybody is
tired. Yes, I understand. No problem. We can go if you want.
So, Paolo, what do you think is the most exciting future direction for this work? Can you apply this to other concepts rather than observability of the position, maybe other parameters, maybe identification of other parameters and in other models?
Yes, I think that there are several possibilities to extend this problem also to other problem. For instance, yes, we can consider because I mean, if we consider just the problem of state estimation, the active sense is not very interesting because usually we have always a lot of sensory measurements that we can use. So the problem is more than observable. But when we consider also self-calibration problem, reconstructing the environment, or even consider that you are applying a control law to a robot that you know. You don't know because, for instance, you don't know what is exactly the model or what are the joint and the actuator. So you need also to identify, for instance, what is the dynamic of this robot. Maybe in this case, you can apply some sort of active sensing in order to determine not only parameter, but also the structure of the robot. And then starting from that, you can apply your control law for accomplish a particular task. But I think also for a multi-robot system, it could be very interesting to find how we can decentralize this optimization problem and see how the robot can cooperate in order to maximize information about something that is interesting for the task.
Okay, thank you.
You're welcome. Okay, Manolo, we can stop here maybe.
Okay, so maybe we can close with this. If you can, Manolo, can you remove the share screen?
I think Paolo is still sharing. Okay.
Okay. So would you like? I think we would like to conclude now. It's let me just do this. And on behalf of all the organizers, am I sharing now? Yeah. This is it. Yeah, so as the elder colleague in the group of organizers, I will just close the session. I would like to thank Paolo, Manolo, Matteo, Manuel, Giorgio, Lucia, for all the colleagues for organizing this jam session this year again. And it's been quite interesting to me. I hope it was also for you. I'm sure that Carlo Trompetto maybe didn't quite understand the tiniest details of Paolo Salaris' talk, and probably the same way, the other way around. Still, I think there is value in listening to other fields and listening to ideas that come from other cultures, if you want. And this is what robotics is about. It's about interdisciplinarity, is about a melting pot that brings different people together. That's what makes robotics so exciting to me. This is the conclusion for this robotics research, and and see you next year, hopefully in person. All the speakers this year are welcome to come again next year, possibly in person. It's a beautiful time in the year, and in Tuscany, it's a pleasant experience. So video is okay. We will not leave this because I think we had many people connecting from far away, many more than could have been in person. So we will do this streaming every year, but we will not give up the convivial and the social occasion of meeting together. So thank you, everybody. Have a good good lunch now, and best luck in the future. Bye bye. And thank you again very much, everybody.
Thank you, Antonio.
Thanks so
Thanks
much
to all the group of Pisa.
Grazie a tutti. Thank you.